this video, we'll learn to read, write, order and compare numbers up to 1 million. If you need to recap on how to write and read numbers up to 1,000, go back to the entry 3 videos. So I've got a number here which I read as 1,111. So this one here at the end represents the units, or single pound coins if this was money. So that would be £1, this would be £10, this would be £100, and this would be £1,000. How would we read this number? 2,536. Because this is the thousands place, this is the hundreds, and this is the tens, and this is the units. You've probably seen a comma that separates hundreds from the thousands, and I always encourage you to use that comma, and I'll use it myself because it makes our life easier when it comes to reading and writing numbers that are large. So we've got 2,536. Now, how do we read this? How do we read this? So 4,036. So there are no hundreds, but we've got to have that zero, because if you don't do that, then the 4 will come over here to make this a 400. But in fact, it was actually 4,000. And it's not the same to have £400 as having £4,000. So this is why you put a 0 there to hold the place. Similarly, you'd read this number as 4,006, whereas this number would be read as 4,030. So it's always worth remembering these labels at the top. So where, or the position, where are the units, where are the tens, where are the hundreds, and where are the thousands. Now what I'm going to be doing, I'm going to be trying to push this further. So I'm going to add a few more digits on this side so that we can try and read and write those numbers that are larger than these. So what I'm going to do here is I will add a 1 here. What is that value? Now, what I said before is that this separates hundreds from the thousands. So these are actually thousands. And we have 3 digits here, so up to 3 digits, we're going to call them thousands. So what does that mean? If I were to hide this, well, how would I read this number? It would be 11. So I'm going to say 11,111. So this is the units of the thousands. This is the tens of the thousands. So tens, thousands. So that is worth 10,000. So now if I add a 1 here, this is going to become 12,536. 64,036. 24,006. 74,030. So again, that's tens of the thousands. If I add 1 more digit, then similar pattern, 111,000 and 111. So this is the hundreds of thousands now. So notice the pattern: units, tens, hundreds; units, tens, and hundreds of thousands. So this would be 612,536, and this would be 464,036. This would be 324,006. This would be 174,030. What would happen if I change this into a 0? And again, I've got to hold the place because otherwise this won't go into the tens of thousands, and that's not the case. This is 100,000. So I can read this as 104,030. Or I could read this as 100,030. Now we'll push it with one more digit. But first of all, what would be that number? That would be one less than a million. So if I continue adding up more and more, so let's say I have 900,000. I'm very close to a million, but not there yet. So the highest number before reaching a million would be 999,999. So if I add just one more, let's say pounds, if I add one more pound in here, this will become 1 million. And how do we write 1 million? So in groups of 3, in groups of 3. So this is 1 million, a 1 with 6 zeros. So the value of this digit here is a million. So this number here would be read as, again, put in the commas now because we put the commas after every 3 digits. Just like we did here, 1, 2, 3, comma, 1, 2, 3, comma, and then 1, 2, 3, comma, if you want to continue with larger numbers. So we got now 1,111,111. And the next one is 4 million. I see I've got 2 commas, so there must be 4 million. 4,612,536. 8,464,036. 3,324,006. 9,999,999. So this is the largest number we can have before we go to billions, but we won't look at billions in this video. We'll look at level 2. So what would happen now if I had a 0 here instead? How would I read this? So again, very similar to before, 3,024,006. And this would be 8,404,036, and this would be 4,610,536, and this would be 4,610,000. That's it, because I have no hundreds, tens and units. So 4,610,000. So this shows how to read and write numbers. Now we'll look at how to compare them. So let's compare the numbers that we have here. Which one is the biggest and which one is the smallest? So we've got 1 million, as we said, 1,111,111. Now which one is bigger out of these two? This is bigger because it's more than 1 million. This is just 1 million, but here I've got 100,000, I've got 10,000 as well, and I've got 1,000, I've got 100, I've got 10, and I've got a unit as well, so £1 as well. So this would be the smallest, and this would come next. Now, which one of these comes next? I'll look at the millions first because they have the biggest value. So if I have 3 million, that means that I have more than a million, more than 2 actually, but this is less than 4 and less than 8 million, that's a 9 million. So you look at the digit at the front first because they have the biggest value. So this now is 3,024,006. So this would come next. So this is the first from the smallest, this is the second, this is the third, and the next one would be this one, 4,610,000, because 4 million is bigger than 3 million, but it's smaller than 8 million or 9 million. So 8,404,036 would come after that. And finally is the 9,999,999. So this is the order from the smallest to the biggest. I'm going to change these numbers slightly now and reorder them again. So if I take off some of these, let's see what happens now. The order will change. Not all of these are millions now. So we've got 1 million, 1,111,111. We've got 10,000 here. We've got 404,036. So that tells me, because it's got more digits, and more digits in this direction have a bigger value. So we've got 404,000 as compared to 10,000 only. So this has got a bit bigger. Now let's order them from the biggest to the smallest. So the biggest one is the one with more digits and a bigger digit at the front. So if we compare them, this is a million, this is more than a million, this is 3 millions. So really, this is the highest, because none of these reach a million anyway. So we've got, this is the highest one. Now which one would come next? Again, we stick with the millions. We've got more digits here, greater value. So comparing them to, as we said, this one would be bigger because it's more than a million, and this is just a million. But this is bigger than 10,000. This is bigger than 404,036, and this is bigger than 9,999. So which one now out of these three is the biggest? Again, so this is 9,000 and something, this is 10,000. Actually, the difference between them two is just 1. So £1 would be the difference between them two. So that's 9,999. This is 10,000. This is 404,000. So this comes next, and then this, and then finally this one. So what we looked at is which one of the numbers has more digits, and then comparing those digits. Like these ones had most of the digits, but there we have 1, there we have a 1, and that was a 3, so we stuck with a 3. Then comparing these two, which have the same digit, we looked at the next one. This is a 0, but this is a 1, so this must be bigger. And then we looked at the one that has more digits out of the 3, and obviously out of these 3 it was this one, and then this one, and finally 9,999. This should help you with working out amounts and reading and writing, ordering and comparing numbers up to a million, and you'd be lucky if that was pounds, but it could be anything else really. It could be grams that we're talking about, kilograms, whatever we're working with. these numbers are always useful at this level. In this video, we'll learn to recognize and use positive and negative numbers. So I've got a thermometer here, which shows positive and negative temperatures. Positive and negative numbers are the same. Actually, temperatures are described using positive and negative numbers. So we've got a 0 at this point, and then we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40 degrees, we could go 50 and so on. Underneath that, there comes the negative part. So imagine 0 degrees in the winter when it's really cold. If it gets even colder, it goes to -1, -2, then -3, -4, -5, then 6, -6, -7, -8, -9, -10, -20, -30, and so on. So the negative numbers are the one with a minus in front, and they are much smaller, as I said. So in the winter it's much colder when we've got negative temperatures. Sometimes you will see these in number lines, so the number line looks very similar to thermometer. You've got the 0, you've got 1, 2, 3, 4, 5, 6, and so on. So that's positive. It means +1, +2, +3 as well. Positive numbers, so they're the same. Then we have -1 under 0, -2, -3, -4, -5, -6, and so on. But you might see a number line that is horizontal as well, and it means exactly the same thing. So 0, there we go in the positive direction, 1, 2, 3, 4, 5, 6, 7, 8, and so on. And then -1, -2, -3, -4, -5, -6, -7, -8, and it continues. So these are the positive temperatures and these are the negative temperatures. These are the positive numbers, these are the negative numbers. So recognizing them is easy. If they have got a plus sign in front, to say +6, it is the same as 6. Even if they don't have it in front, the number doesn't have the plus sign in front, it means the same thing. But if you see a -6, that means a negative number. A minus always has the sign in front. A negative number always has that minus sign in front of the negative sign in front. So you can read this as -6 or -6 as well. It means the same thing. Now we can recognize them. How do you use them? So you might have questions typically relating to temperature or being overdraft. So if the temperature is 0 and then so it's 0 degrees and then it drops by 4 degrees, what's going to happen? So we go 1 step, 2, 3, 4 to go to -4. So 0 minus 4 equals -4. And then if we are on -4, so we go -4, if it goes then up the temperature, let's say by 5 degrees, so we add in 5, what's going to be happening? So we go 1 step, 2, 3, 4, 5 steps upwards. So from 0 we go to 1. So -4 plus the 5 equals 1. Now we are on 1 degree Celsius. What is going to happen then if the temperature drops by 11 degrees? So 1 minus 11, what's going to happen? So we move 1 step to go to 0 and another 10 steps, and this goes to -10. So we've got a minus 10 degrees temperature in there. This works also for being overdraft. So let's say you have a balance of £0 in your bank account and you withdraw £4, then you are overdraft by £4. So you owe £4 to the bank. And if you are then at that point when you are overdraft by £4, you top it up by £5, so you add to your account £5. What you're left with is £1 because obviously that 4 was used, the first 4 were used to compensate for this. And then we have, with that £1 that you have in your bank account, if you withdraw another 11, what you end up with is being overdraft by £10. So the way to do this is really to start, where are you at? So that first number always tells you where you're at. So you can refer to temperature or money, whatever you prefer, but these are the two easiest ones. Even other ways you could use, but these are the two easiest ones that we use in everyday life. So we start with, where are we at the moment? Okay, 0 in your bank account, or 0 degrees Celsius in the winter, whichever you prefer. And then drop by 4, take away 4, withdraw 4, and that gives you the answer in the end. And I would always prefer to refer to a number line because then you can't get it wrong. So we start from 0, it means dropping 4 degrees or going down by 4 or withdrawing 4. So I'm going to make 4 steps. So 1, 2, 3, 4. Where I'm at minus 4. Then I've got minus 4, I'm going to add 5. So right, I am here, I'm going to go up by 5. So 1, 2, 3, 4, 5. And that is 1. So, and this tells me whether I go up or down. So minus means you go down, dropping, withdrawing. Add means going up. So I am now at 1, and I'm going to drop this by 11, take away 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now I didn't continue adding the numbers in here, what I could do now. So minus 7, minus 8, minus 9, and minus 10. So this shows how to recognize and use positive and negative numbers. In this video, we'll learn to multiply and divide whole numbers and decimals by 10, 100 and 1000. We need, and we use this skill in everyday life when it comes to working out the cost of 100 items, 10 items or 1000 items, or sharing out costs between 10 people, 100, 1000 maybe. Now, how is this different from multiplying by 8, 9, 19, 29? This is what we're going to look at, because there is a pattern which makes multiplication and division by 10, 100 and 1000 very easy. So I've got some whole numbers at the top and some decimals at the bottom. Before I go through multiplying and dividing, I'd like to show you this timetables grid. And I want you to look at what happens when you multiply 1 by 10, the answer is 10. 2 by 10, the answer is 20. 3 by 10, the answer is 30. 4 by 10, the answer is 40. So look at these digits and look at these digits here. We've got 1, 2, 3, 4, 5, 6 and so on, and that's been repeated here as well. 1, 2, 3, 4, 5, 6. But what we have is a 0 at the end for all of these numbers, because every time you multiply by 10, a whole number, this is what happens. You add a 0 at the end. So 8 times 10 is 80. So what do you expect is going to happen when you multiply 15 by 10? I'll write 15 as it is, and I'll add the 0. So that becomes 150. We've got 275 times 10. So 275 rewritten, and add the 0 from the 10. So that's what happens when you multiply a whole number by 10. You just add a 0 at the end. Because if you look at it, the number has got bigger. 15 lots of 10 is 150. 275 times 10 gives you 2,750. So by adding that 0, we're making the number much larger, actually 10 times larger. 15 times 100. What do you think is going to happen now? Now, I underlined the 0 when we multiplied that by 10, so I'll underline the zeros again when multiplying by 100. So I'll write 15, and I'll add this time not 1 0 but 2 zeros, because there are 2 zeros in 100. And look at the number, it's become 1,500. So 100 lots of 15 make 1,500. 275 times 10 times 100 this time around. So I'll rewrite 275, add the 2 zeros at the end. So this becomes now 27,500. Now I'm multiplying 15 by 1,000. So I'll rewrite 15, and there are 1, 2, 3 zeros in 1,000, so that becomes 15,000. And indeed, 15 lots of 1,000 gives you 15,000. Now I've got 275 multiplied by 1,000. So I'll rewrite 275 and add the 3 zeros. So 275 lots of 1,000, that gives us 275,000, and that's what we have as our answer. So to summarize, when we multiply whole numbers, this is 15, 275, 2, 7,000, so it's whole number, not a decimal. Then if we're multiplying it by 10, we add a 0 at the end. If we're multiplying by 100, we add 2 zeros. If we're multiplying it by 1,000, we add 3 zeros. So underline the zeros in the number you're multiplying it by. Now we'll look at dividing these whole numbers. So I've got 25,000 divided by 10. Now, if I want to work this out, I need to again go back to the grid that I had. So if you look at it, we had this answer, and when we divide by 10, what do we get? So it's the reverse of the process. So 10 divided by 10 gives me 1. 20 divided by 10 gives me 2. 30 divided by 10 gives me 3. So what's happening? I'm actually now knocking off the 0. I'm reversing the process, which means knocking off the 0. And that's what's going to happen exactly here. So we've got the 10 has 1 0, so I'm going to knock off only 1 0 of the number. So I'll rewrite this as 2500, which is 2,500. And we've got 4,500 here divided by 10, so knocking off a 0, that gives me 450. We've got 25,000 divided by 100. So now I'll need to knock off 2 zeros. So I'll go, that's it up to this point. So we've got 250 as the answer. Similarly, here we've got 1, 2 to take away, so our answer will be 45. So as you can notice, the actual answer is getting smaller. The number is getting smaller. From 25,000 divided by 10, that gave us 2,500. How can I check I've got it right? 10 lots of 2,500 gives me 25,000. So 25,000 divided by 1,000. 1,000 has 1, 2, 3 zeros, so I'll knock off 3 zeros. So they go 1, 2, 3. So the answer is 25. 4,500 divided by 1,000. So 1, 2, 3 zeros. So we go 1, 2. Now this is a 5, so I can't really knock that off. So what I'm going to do, I'm going to write the answer as 4.5. And how does that make sense? If I had 4,000 divided by 1,000, what would my answer be? So I'd need to knock off 1, 2, 3 0. So 1, 2, 3, and I'd be left with just 4. But in actual fact, I had 4,500. So 4,500. So that's what is going to happen to the answer here as well. I can't just have the 4 here as my answer because I've got another half to take care of. So that's why I write this as 4.5, which means 4.5. We'll have a look at what exactly that means in another way when we now deal with decimals here. To help us understand how to multiply and divide decimals by 10, 100 and 1,000, I'm going to use one of these previous examples with whole numbers. So what I'm going to do, that was 15 times 10. I'm going to write 15 as a decimal. So I'll write it as 15.0. And as you know, 15.0 is exactly the same as 15 because this tells me I've got 15 wholes and 0 parts. If this was money, 15.000 would mean that I would have 15 whole pounds and no pennies. So those zeros after the decimal point have really no value. So what I'm going to be doing is I'm going to use this scenario to multiply by 10. So 15.00 times 10. What is going to happen here? What if you try this with a calculator or by hand, you'll see that this will give us 150 or 150.0, which is the same answer. So what has happened? I'm multiplying by 10. So, and we're talking about positive numbers here. So that means that my answer will get bigger, 10 times bigger. So this decimal point here has moved 1 place to the right, which is the positive direction in number lines or thermometers. If you recall, so there is 0, here is the positive ones, positive numbers, and there is the negative numbers. So this is what's happened to 15.00 times 10 gives us 150. So exactly now, or very similar to this, will be this. If I do 15.00, not trying out this one, times 100. So I'm going to move, because I'm multiplying, I'm moving in the positive direction and the number will get bigger. So we go 1, 2 places because there are 2 zeros in the 100. So this number now will have the decimal at the end. So it's going to be 1500. The decimal is invisible now because it's a whole number, and you can add it if you want. and put zeros, any more zeros, but it won't make any difference because the number has the same value. So this is 1500, this is 1500. I did this so that it can help us with the rest of the decimals. So 1.5 times 10. Which direction are we moving? In the positive direction because it's multiplication. How many places? It's going to be 1 place. So that decimal, which is now here, is going to move 1 place to move there. So if we have no digits, we can add a 0 or just take away the decimal point in this case, because we don't have any digits after the 5. Now we've got 1.5 times 100. So again, multiplication means moving in the positive direction, making the number bigger. So we go, I'll write 1 and the 5. The decimal is at this point here between 1 and 5, but it needs to move 2 places in the positive direction. So 1, 2. So it's going to be now there. But there is a space there that's not filled. So what I'm going to do is put a 0 in. And that is right at the end of the number. So that means 150. So I can take it off completely. 1.5 times 1000. So means moving in the positive direction 3 places. So from here we go 1, 2, 3 places. So there we go, we have 2 empty spaces to be filled with zeros. So this becomes now 1500. Let's have a look at this one. 27.5 times 10. So 1 place we're moving in the positive direction. So 275, it is here at the moment, we're moving 1 place and it becomes 275. 0.5 times 100. So right there we have 0.5. We're moving 2 places in the positive direction. So we go 1, 2. So decimal moves there. So we need to fill this space. And does that 0 need to stand there now? Because there is no decimal point in between them. The decimal point is at the end. No, it doesn't. And the decimal point doesn't even need to be there because this is a whole number. So we got 50 as the answer. What about this? So we have these digits, 2704. We're multiplying by 1000. Decimal point is here. So we go 1, 2, 3 places. So decimal point will move to that point. So that doesn't exist anymore. And this is a whole number with no digits after. So we'll have this as 27,040. We'll now look at dividing the decimals by 10, 100 and 1000. So if I refer to the examples that I used before, so I went 15.00 times 100 gives me 1500. Now division is the reverse process, so I'm going to go 1500 divided by 100 gives me 15. So when I reverse this, what's happened? If you look at the decimal point, which would actually be here, when I divided it by 100, it moved 1, 2 places. So 1, 2 places to become 15. So what are we learning through this? Is that the number of places you're moving, again, depends on how many zeros in the 10, 100 or 1000 that you're multiplying by, and which direction you move in really depends on what you're doing, what's the operation. So when you multiply, you move in the positive direction. When you divide, you move in the negative direction to make the number smaller. So 4.5 divided by 10. So I'll rewrite the digits 4 and 5. At the moment, the decimal is between 4 and 5, and it's being divided by 10. So divided means moving in the negative direction to make the number even smaller. So we go one place to the left because there is 1 0 in the 10. So the decimal point will be here now. But can I have just 0.45? Mathematically, you need to add a 0 in front. So this becomes 0.45. Now, 4.5 is going to be divided by 100. So again, divided means moving to the left, and it is 2 places. So we go 1, 2. The decimal point must be there. There is a place unfilled, so I'm going to fill that with a 0. And in front of the decimal, I need a 0 as well. So 0.045. Now 4.5 will be divided by 1,000. So divided and moving 3 places. So we go 1, 2, 3. So it's going to be there. Now we have 2 places unfilled. So 1, 2. That decimal is moving from there, and we need a 0 in front to make this into 0.0045. So I'll bring the 5 a bit closer here. And 75.3 divided by 10. So 75.3 divided means we move into the left, and by 10 means we move in 1 place. So I'm going to go 1 place. There we go. So the answer now is 7.53. 8.4 divided by 100. So we move into the left 2 places. Go 1, 2. There is a blank space there that needs to be filled, and of course a 0 in front of the decimal. So this becomes 0.084. 4.0 divided by 1,000. So we move in 3 places. To the left we go 1, 2, 3, and this is where we stop. So we fill these with zeros, and we have a 0 in front. So this becomes 0.0040. So this, I hope, has shown you how to multiply and divide whole numbers and decimals by 10, 100 and 1,000. In this video, we'll learn to use multiplication facts and make connections with division facts. If you've forgotten how to multiply or divide, go back to the entry 3 videos in these topics. What I will focus on in this video is the connection between multiplication and division. So let's start with an example. I've got 5 rows of small cubes, and there are 10 cubes in each row. So we've got 10, and another lot of 10, and another, and another, and a final lot of 10. So 5 lots of 10, or 5 times 10. That gives us a total of 50 small cubes. So I've multiplied these two numbers to get the product, which is 50. I could have said 10 lots of 5 as well, because what I've got is 10 columns of 5 in each column. So either way, that would give us the same answer, that total of 50. And it is in a way like adding on. So we said 10 and 10 and 10 and 10 and 10 makes 50, or adding 5 and 5 and 5 and 5 and so on to make 50. Now I'll get the same number of cubes, which is 50. So that total which we had there, we'll get it here. That final answer we had there, I'll get it to the front now. So I've got 50. I haven't done anything to them. All I know that this is the total. So what am I going to do with this 50 cubes that I have? Now I might decide to share them into 10. So I'm going to give them to different people, 10 to each person. So let's see how many people will be able to get 10. So if I share into or divide by 10, I'll have 1, 2, 3, 4, 5. So the answer is 5. Or I could get this 50 and share it into 5s. So let's see, I've got 5 in the first row, in the second, and so on. So how many rows do I make of 5 cubes each? So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what this tells me is that multiplication and division are opposites of each other. So we started with 5 times 10 and it gave us 50, or 10 times 5 and it gives us 50, that total, that bigger number over there. Now that bigger amount has been shared into 10s or divided by 10, and it gave us 5. So what I'm doing is reversing this process here. I go 50 divided by 10, because multiplication and division, as we said, are opposites of each other. So 50 divided by 10 gives me 5, or 50 divided by 5 gives me 10, and that is what's happened. Or if I reverse this, so we know that multiplication is the opposite of division, so I go 5 times, so instead of division I go times. 5 times 10 gives me 50. 10 times 5 equals 50. So how does this help us? Let's say if I do 12 times 6, so work it out. So I will go 6 lots of 2 is 12, so 2 down and 1 carried over. 6 times 1 is 6 and the 1 is 7. So I've got 72 as my total. Now I can reverse that process to check that I've got this calculation right. So I go, right, this is the total, 72. If I divide this by 6, does it give me 12? So again, doing the reverse. And let's see. So how many 6s fit into 7? That is 1. And there is 1 left. How many 6s fit into 12? That's 2. So that gives me 12. That proves that I did the calculation right. Or if I start with division, let's say I've got 540 and I need to divide it by 4. So let's do it. How many 4s into 5? That's 1. And we have 1 left. So how many 4s into 14? That is 3, because we've got 12. And then 5s into 20, there's 5 of them. So 135 is the answer for that. But how can I make sure I've done the calculation right? So I do the opposite now. I've got 135 times 4. So 4 lots of 5 is 20, 0 down and 2 over. 4 times 3 is 12 and the 2 is 14, so 4 down and 1 carried over. 4 times 1 is 4 and the 1 is 5, so 540, which matches the number that we started with. So that proves I've done the calculation right. So how do we know which operation to use, multiplication or division? Then you look for questions where you've got to multiply, or it's lots of different things. Let's say shopping. If you buy 8 bags of £12, then you know that you're going to be multiplying 8 by the price of each bag and get the total. Or if you've got a budget of £100 and you want to buy as many books as possible, or as many, let's say, frames as possible, picture frames as possible. If one picture frame costs £5, then you've got to divide that 100 by 5 to get how many picture frames you can buy in total, or whatever you're buying. So you look for keywords such as times, or lots of, or shopping, or total, to decide what to go for. Place yourself in that situation and solve the problem. In this video, we'll learn to use simple formulae expressed in words for 1 or 2 step operations. Now, this might seem like a complicated thing, but we use this in everyday life. We do it. So I'll start with 1 step and then move to the 2 step operations. Here is an example. To write time in the afternoon in the 24-hour format, add 12. So we've got time, PM means in the afternoon, and you're writing it in a 12-hour format. So let's say it's 2 PM. If you add 12, that makes it 14. So this has given us the time, the same time, in the 24-hour format. And you could change this, so let's say if it's 5 PM at 12, it's going to give you 17:00, which is the same time in the 24-hour format. So this is one example. And as well as going this way, you should be able to reverse the process. So what I'm going to be doing now is, let's say you're given the time in 24-hour format. Let's say it is 21:00. Now we need to find what was the time in the 12-hour format in the afternoon. So we've got 21, reversing. Initially we added 12, now we're going to take away 12 because we know that addition and subtraction are opposites of each other. So now going this way, I'll do minus 12. So 21 minus 12 gives me 9. So there we go, it's 9 o'clock. So it works both ways. Now 9 at 12 gives me 21. 21 take away 12 gives me 9. So you might be given time in the afternoon in a 12-hour format expressed with PM, or you might be given time in the 24-hour format. So either way, if it's here, you're going to go and find that hour, that time missing there, and if you are given the time in the 24-hour format, you reverse the process to find the time in the 12-hour format in the afternoon. Other examples include converting measurements from centimeters to meters or centimeters to millimeters. So it might be in words that to convert from centimeters to millimeters, you need to multiply by 10. So if you're given 5 centimeters, times 10 times 10, that makes 50 millimeters. Or maybe you're given centimeters to convert into meters, and in this case you need to divide by 100. So let's say you have 550 centimeters, divide by 100, we go 1, 2 steps, so that is 5.5 meters. Now the two-step operations. I've got an example here. Jane uses a taxi to get home from college. The taxi company charges a 55 pence per mile and a 90 pence booking fee. So we've got the number of miles to be input. So let's say if it's 2 miles, then you multiply by 55, which is the pence per mile, and add 90, which is again pence, so we can have it missing in here, and we've included pence in the final answer, so cost of the trip in pence. So the question might ask, Jane's trip is 3 miles long. The distance between the college and home is 3 miles. So work out the cost of the trip. So if this is 3 miles, then we go 3 times 55. Three times 5 is 15, so 5 down and 1 carried over. 5 times 3 is 15, and that one, so 16. So 165 pence, that's so far. Now we've got to add 90 to that, so we've got 165 at the 90. 5, 15, 255. So that brings it here now, 255 pence. So that is the cost if Jane travels 3 miles. It could be 4 miles, 5, so whatever the number of miles, if you follow these steps in order, you should get the answer. You should get the answer. So another question you might be asked actually is the cost of the trip is 255 pence. So we don't know how many miles, and we've got to work it out. But how would we do it? If you remember from the previous video, if the answer is here in the output, then we've got to reverse the process. So I'd go 255, take away 90, and then divide by 55. And that gives me the number of miles. So let's have a look. So 255, take away 90. What does that give me? $165. So 165 is here. Now what do? I divide by 55. So the opposite of multiplication is division, and we don't change the number. The opposite of addition is subtraction, and we don't change the number. So plus 90 minus 90 times 55 divided by 55. So 165 divided by 55. How many 55s would fit into 165? So I know for definite 1 does. If I add another 1, that is going to be 110, but I can fit another 55, so 55, that's 565, so it's exactly 3. So that gives me the answer of 3 miles. So it was really important to follow the steps, because otherwise you'd get a different answer. If you added first 90 and then multiplied the answer by 55, it'd give you a completely different answer, a larger number. So we don't want that. We just want to follow the steps. Another example is that of currency conversion. So if you go to a shop and they charge a fee for converting the money, then they've got their currency rate as well applied. So that's what you need to do. Maybe deduct from your money the fixed amount they need to pay first, and then do the conversion. So there are different examples in everyday life. We use this maybe on a daily basis, and it's something that we need to improve on by doing more and more examples. In this video, we'll learn to calculate the squares of 1-digit and 2-digit numbers. So what are square numbers? Square numbers are the numbers which, when you multiply by themselves, create squares. So if you look at this one here, 2, there are 2 centimeters at the bottom, so 2 centimeters one side and 2 centimeters the other. The area is actually 4 centimeters squared. And here we have 3 centimeters by 3 gives you 9. So 9 is the square of 3. 9 is a square number. So there is 4 times 4 gives me 16. 5 times 5 gives me 25. 1 times 1 gives me 1. So these are the first square numbers. 1, 4, 9, 16, 25. What could be the next one? 6 times 6 is 36, so 36 is the next square number. 7 times 7 is 49, so the square of 7 is 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. So how do I write this? 1 times 1 is the same as saying 1 squared. What does that mean? It's 2 lots of 1 we're multiplying with each other. Then we have 2 times 2 is the same as 2 squared, and that gives me 4. 3 times 3 is equal to 3 squared, or 9. 4 times 4 equals 4 squared, which gives us 16. So I'll write it here. 4 times 4, 16. 5 times 5 equals 5 squared, or 25. Now these are just the first few. Now I could also work out what is the square of 12, for example. So 12 squared. Now that 2 at the top means we're multiplying 2 lots of 12 with each other. So that is 12 times 12. And that is 144. What about 25 squared? So that means 25 times 25. And we'll need to work that out. And how do we do that? There are different methods you can use. I'm going to use the column method here. 5 times 5 is 25. 5 times 2 is 10, and the 2 is 12. Now we're moving down, so we need to add a 0. 2 times 5 is 10, and the 1 carry it over. 2 times 2 is 4 and the 1 is 5. So that is 625. So the square of 25 is 625. In this video we'll learn to follow the order of operators or operations. Operators or operations are addition, subtraction, multiplication and division. They tell us what to do with the numbers. Like this one here. 5 times 4, or 5 lots of 4, plus 3, or add 3. And there we have 3 add 5 lots of 4, 5 lots of 4 take away 3, and 3 take away 5 lots of 4. So what do we notice? When I read this, I'm saying 5 lots of 4. So it is like a block that cannot be separated, because we cannot say 5 lots of nothing. So these two numbers go together because this is telling me how many lots of this or how many lots of this there are. So I imagine this like a block, and I've shown it here. So it's 5 lots of 4, and then add onto it 3. So that's like an add-on thing at the end. So I've got the block 5 lots of 4 and add 3. So that meant I did multiplication first and then added. And that was the order of operations here as well, because we had multiplication first and then addition. But does it mean that when we have addition first and multiplication, then do we do addition first or multiplication first? So let's have a look at that. So we've got, as I said, 3 add 5 lots of 4. As you notice again, I'm saying 5 lots of 4. So that means I've got a block of 5 lots of 4. And I'm adding 3. Or I could have had that to begin with and then add 5 lots of 4, which is 20. So the total is 23 in both cases. So what did we learn through this? It was that we do multiplication before addition. The order of them appearing in the sentence, in the math sentence, does not matter. It could be that addition is first in the sentence or it's last, but still we do the multiplication first. So 3 add 5 lots of 4 is like saying 3 add 20. So I'm working out 20 first, then adding 3 to make 23. What happens with subtraction? Which one do we put first, multiplication or subtraction? So let's have a look. So again, 5 lots of 4 take away 3. So again, we have that block there, 5 lots of 4, which was 20. Take away 3 gives us 17. And here we have 3 take away 5 lots of 4. So again, 5 lots of 4 we work out in our heads or underneath. So I could do 3 take away 20. So we're going into negatives here. If we have a temperature of +3 and that drops by 20 degrees, it's going to go into the negative. So that's going to be -17 or -17. So notice the difference. When we had 3 in front, then we just changed the sign in front of the 17. So that was 17, this is -17 or -17. So again, even between multiplication and subtraction, multiplication takes priority. So we can safely say that multiplication comes first before addition and or subtraction. So what we're going to look at now is division and addition. So I'm going to write 20 divided by 4 add 3 and 3 add 20 divided by 4. Is it the same rule as with multiplication? So I read this as 20 divided by 4 add 3. So again, I imagine having 20 small cubes divided into 4, and that means I have 5. So 5 add 3, so I've done this for first to give me 5, add 3, that gives me an answer of 8. And if I look at this one, we've got 3 add 20 divided by 4 again, so that means I'm dividing that 20 into something, so I haven't finished with that 20. I can't just take it for granted and add it to 3, because I'm going to do something to it. I'm going to share, I'm going to divide it, whereas addition means you can add it on top. So what I'm going to do is 3 add 20 divided by 4, which is 5. So that means we've got 3 add 5 to give us again 8. So division and addition, when we've got them in the same sentence, we do division first. Is it the case with subtraction though? So I will put down 20 divided by 4 minus 3 and 3 minus 20 divided by 4. So again, 20 divided by 4, I'm doing something to the 20, I haven't finished yet, so that means I'm sharing that to give me 5. 5 take away 3, that gives me 2. And we've got 3 take away 20 divided by 4, so we do the division first, so that gives us 3 take away 5 to give us minus 2 or negative 2. So again, division has priority over addition and subtraction. So we know that they will come first and addition and subtraction will come after, will come next. But between them two, is there any rule of priority? And between them two, which one comes first? So that's what we're going to be looking at now. So let's take an example. We've got 20 divided by 2 times 5. So let's try doing division first. So 20 divided by 2 gives us 10. And then times 5, that gives us 15. Whoa! And another example for addition and subtraction. So 4 take away 3, add 5. So when we have multiplication and division in one math sentence, we just follow the order of which one comes first, just like reading a sentence. So 20 divided by 2 is 10, times 5 is 50. And addition and subtraction, so 4 take away 3 is 1, add 5 is 6. So just follow that order. So to summarize, Multiplication and division come before addition and subtraction, and we've looked at the reasons why. Within multiplication and division, they are equals, and you just follow the order that they present it in, just like reading a sentence. And the same thing happens within addition and subtraction. Just follow the order they are presented in. Sometimes we have some of the numbers in brackets, and that changes things. That changes the answers that we get. So we had this 5 lots of 4 at 3, and it gave us 23 because multiplication came first. But if I have 5 lots of, open the bracket, 4 add 3, and then close the bracket. So that means I've got 4 at 3 together within the bracket. So I've got to do that first. So I have 5 lots of 4 add 3, which is 7. So 5 lots of 7 gives me 35. So brackets come before multiplication and addition. So again, over here, although multiplication comes first when you don't have brackets, if I have 3 at 5 in brackets and then times 4, I'll do the brackets first. So 3 at 5 giving us 8 times 4 gives us 32. And 5 lots of 4 minus 3, that means 5 lots of 4 minus 3 is 1. 5 lots of 1 gives us 5. And if I had here, let's say 3 minus 5 in brackets times 4. So 3 minus 5, or 3 take away 5, gives us minus 2. Minus 2 times 4, or 4 lots of minus 2, gives us minus 8. And if I have 20 divided by 4 add 3, and that is in brackets, so we'd be looking at 20 divided by 7. So that's about 2.9. And on the other side, if we had 3 at 20 in brackets divided by 4, so that would mean 23 divided by 4, which is 5.75, and 20 divided by 4 minus 3, that is 20 divided by 1, which gives us 20. And finally, if we had 3 minus 20 in brackets, then divided by 4, that means we do 3 minus 20 first, which is minus 17, and then we'll divide that by 4. So that will give us minus 4.25. Don't worry too much if you can't work with those negative numbers. It's just here to illustrate with examples what it means when you actually have brackets in some of the math sentences. In this video, we're going to read, write, order and compare common fractions and mixed numbers. So we've got half, a quarter, 5/6, 12/7, 1 and 4/5, 2 and 5/8. So I've written them and I'm reading them as well. So this should help you with the reading of the fractions. So did you notice 5/6? So GHS at the end, not just 6, 5/6. 12/7, 1 and 4/5, 2 and 5/8. So also there is a difference with these two at the end. We've got 1 4/5. So that means a whole one, maybe a whole pizza and 4/5 of a pizza, 2 pounds and 5/8 of a pound. So that shows in front how many whole parts we've got, how many whole measurements, how many whole shapes we have. So this is why we call them mixed numbers, because we've got whole numbers and fractions. Now we're going to try and compare and order them. So in order for them to be compared, they need to look similar to each other. What do I mean by that? So at the moment we've got 1/2 and 3/4. Now we know how these look like and it's easy to compare them. I know that 3/4 is bigger than 1/2 because of what they mean. So this is 1/2 and this is 3/4. So I know that, and at this level we're supposed to know that. But I would find it more difficult to compare these to this, for example. What does that mean? So, or the 12/7, or the 1 4/5, or the 2 5/8. So what can we do? Now what I'm going to do is illustrate what I'm going to change through these two fractions. So that is 1/2, as we said, and we could show it like this. And this was the 3/4. So there we go. We've got the 3/4. I want to show this 1/2 in a similar way into quarters. I'm going to cut it into quarters and pick just 2 of them because that is what a 1/2 is. So I've got now 2 quarters and I've got 3/4. So which one is bigger? Of course, 3/4 is bigger than 2/4. So we're comparing like for like, and we've got numbers at the top that we've got to compare now. So what we call this is making the denominators the same. So down, the number that is down here, denominator. The numbers that are at the top or north, numerator. So that's the way to remember them. So I'll write the words here. Denominator, down. And north, up or north, easy to remember because they begin with the same letter. Numerator. So here is the numerator if you want to remember these. Now I'll try and compare some other fractions. So I'm going to try and compare these two together. Now the way that they look at the moment is slightly different than these two. So we're 5/6. If you look at this, 5/6, we've got a smaller number at the top. So what this means is that we haven't got a whole yet. So if I represent this, this is going to be cut into 6 parts, and I'm taking 4 or 5 of them. So there is a slice left, 1/6 is left. Whereas when it comes to this, 12/7, this is, the number at the top is bigger than the number at the bottom. So it means that I've got more than a whole. So if I show 7/7 first, so I've got 2, 3, 4, 5, 6, 7. So this should have 7 equal parts, and I'm taking the whole of it. And in addition, I've got 5/7 on top. So 7/7 and 5 as well. So 1, 2, 3, 4, 5. So this whole thing, and 5 out of the 7. So just by looking at these two, actually, just by looking at the numbers, this has got to be bigger than 5/6. So I don't need to work it out like I did with the 1/2 and 3/4. But I can see also that the mixed number next to it makes a whole and part of the whole. So I'm going to try and represent this first of all, and then I'll compare them using the numbers. So I will go right. So we've got 1 whole and 4/5. Now if you look at them, they look pretty similar, so I need to be sure that I know exactly which one is the biggest. So what I'm going to try and do is I'm going to try and make this into a fraction. So it's going to look something like this. So I've got a whole, so that's split into 5, and I'm taking all 5 of them. So I've got 5/5 here, and on top I've got 4/5 as well. So adding these two together means that I've got now 9/5. So 9/5 is the same as 1 and 4/5. I need to compare it to 12/7. So 12/7 and 9/5. I need to compare them, which one is bigger and which one is smaller. So in order to do that, I'm going to try and make the denominator the same, just like I did with them too. So this is going to be something that 7 can go into, so a number that 7 can go into without remainder, and 5 can go into as well. So it could be 35. I'm going to try 35 because 7 times 5 is 35, so that's easy to find. And another 35. So I'm going to try and make this now with a denominator of 35. So it is 7 at the moment. To make it 35, I am multiplying by 5. So I need to do the same to the 12. So multiplying it by 5. 12 times 5. 10 times 5 is 50. And 2 times 5 is 10. So that is 60. So 12/7 is the same as 60/35. So now I need to do something similar to the 9/5. So from 5 to go into 35, we're multiplying by 7. So I need to do the same to the 9. So 9 times 7 is 63. So what we're comparing now is very clear. We've got 60/35 and we've got 63/35. So which one is bigger? This is definitely bigger, the 63/35. And so I can say the same for these two then, that 9/5 is bigger than 12/7. And if I compare now 2 and 5/8 with any of these numbers, that's got to be the biggest one. Why? Because we're talking about 2 whole pizzas in this case, or 2 whole meters, whatever you're working out. So that is 2 whole ones, and none of these had 2 whole ones. Look at that, there was a whole 1 and 4/5, and that was a whole 1 and 4, no, it was a whole 1 and 5/7. So none of these had 2 whole ones, so this got to be the biggest one. So if I go and check the order now, if I try and put them in order, 1/2 was much smaller than 3/4, so that was the smallest fraction out of them all. and then 3/4 came next. And because we compared 5/6 with 3/4, and 5/6 was bigger than 3/4, so that must come next. And then we compared 12/7 with 5/6 as well. So 12/7 was much bigger because it means a whole one as well as a fraction. And when we compared them too as well, 1 and 4/5, which was 9/5, was bigger than 12/7. So that must come next. And finally 2 and 5/8, because it's the biggest fraction of them all. So we've got them in order. In this video we'll learn to find fractions of whole number quantities or measurements. So I've got 3/4 of £200, which is something that you might need to work out in everyday life. So maybe something you want costs £200 and it's 1/4 off. How much did you need to pay? So I am representing 3/4 using a circle. So let's assume that this is a pizza that costs £200, so it's a very expensive pizza. And I want to find out how much is 3/4 of it, how much does it cost? So if you look at the pizza, I've cut it into 4 quarters, 4 equal parts, 4 quarters. So that's what I'm going to do with the £200 to find exactly how much each slice costs. So 200 divided by 4, that gives me 50. Or 200 halved gives me 100, halved again gives me 50. So I'll put 50, 50 and 50 here, and 50 as well. So the amount that I need to pay, the 3/4 is made of 50, 50 and 50, which is 150. So 3/4 of £200 is £150. What did I do to 200? I divided it by 4 and multiplied it by 3. Now I've got to find 5/6 of 84 meters. So here is supposedly 84 meters. This is the duration. I've shown it. And I need to find 5/6 of it. So there we go. I've split this into 6 equal parts, 6 equal segments. And where is 5/6? So 5/6 would be here. So what I'm going to do now, since all of this is equal to 84, I'm going to split 84 into 6 equal parts. So I can find how many meters would be in each division. So 84 divided by 6. How many 6s fit into 8? That is 1. And what is left? 2. So 6 is into 24. There are 4 of them. So there are 14 meters in each of these segments. But where do I need to stop? Do I include this? No, I don't. So from this point now, what I can do is I'll do 14 lots of 5, because we've got 1, 2, 3, 4, 5, and that's what the fraction tells us. So 5 times 4 is 20. 5 times 1 is 5, and the 2, that is 70. So 5/6 of 84 meters is 70 meters. How can I check? There is only one part left, so 84 take away 14 gives me 70. So that is how you find fractions of whole numbers, be they quantities or measurements, but you need to also work it out using a calculator. So 3/4 we said is 3 lots of the quarters, so 3 out of the 4. But this line in the middle also means division. So this looks like the division sign in the calculator. So there's a number at the top divided by the number at the bottom. So if you look at the division sign, that's what it looks like. So just like a fraction. Number at the top divided by the number at the bottom. So 3 out of 4 is the same as saying 3 divided by 4. So 3 divided by 4 gives me 3/4 or 0.75, which is exactly the same in decimal form. So 3/4 of 200. So I want 0.75 of 200. So times 200. And that gave me 150. So what did I do? 3 divided by 4 times 150. So what do I need to do here? I go 5 divided by 6 times 84. So 5 divided by 6 times 84. That gives me 70 as well. So when it comes to finding a fraction of a number or a quantity or measurement, all you have to do, look at the fraction. So the number at the top divided by the number at the bottom times by 84. So that's a method useful for when you use a calculator, when you can use a calculator, but not always you can use a calculator. So that's why I showed you the first method of getting the number divided by the denominator multiplied by the numerator. So the whole amount divided by the number at the bottom of the fraction multiplied by the number at the top of the fraction. So I'll say represent it. This is my way of working out. If I haven't got a calculator, I'd represent what does that mean and what is the total amount that we're talking about. Then split it into how many equal parts the fraction has been split into, and then multiply by how many parts you're actually considering or taking or using. In this video, we'll learn to read, write, order and compare decimals up to 3 decimal places. So we've got decimals with 1 decimal place, which means 1 digit after the decimal point, and 0.2 as well is a decimal with 1 decimal place. And then we've got 2 with 2 decimal places, so 1.42, the 4 and 2 come after the decimal point, 0.22, and finally there's 1 with 3 decimal places, so 2.422. So there are 3 digits after the decimal point. So the way we read them are just like I read them. So we go 1.42. We don't say 1.42. No, after the decimal point we read the digits separately. So 1.42, 1.4, 2.422, 0.2, 0.22, and this is how we write them as well. So when I say 1 point, you write the 1.4, so the 4 would come after, or 2.422. You just write the digits as they are read. Now in terms of ordering and comparing them, so this is what I'm going to be working on. So I've tried to represent 1.42 and I link it to money because it's one of the contexts that we use on a daily basis and it's easier to understand and remember. But you could also link it to measurement and a range of other topics. So we got 1.42. If this was money, I'll try and put a pound notation in front just to put it into context. So we got 1.42, and we've said that the decimal point represents the wholes from the parts. So that means that I've got a whole pound, and this is what is telling me that this is a pound, the pound sign in front. So we've got 1 pound, and that there we've got 40 pence, so 10, 20, 30, 40, and there are 2 pence. So 1 pound 42. So if I am trying now to compare that with the 1.4, how much money would I have here? It would be 1 pound and 40 pence, because I haven't got any digit after here to represent the pennies. So I can add a 0 after it. And in other ways, you could look at if it's 1.4, it's a whole one and 0.4. So what is 0.4 of a pound? There we go, 0 to 1 pound, and so I'm splitting it into 10 equal parts. So 0.1, 0.2, 0.3, 0.4, so up to this point. So if this whole line represents 1 pound, how much does one of these divisions represent? And since it's 10 of them, that means 10 pence. So 10p and another 10 and another 10 and another 10, it'll be 40 pence. So that 4 in there means 40 pence. So now I have 1 pound 40. Here I have £2 42 pence, and that 2 at the end represents a smaller amount than a penny. So we're talking about amounts or coins that we haven't got in use today. So, but what we need to remember that this is even a smaller amount. As you can see, it's getting from pounds to 10p to pennies. So this is tenths of pennies. We're talking about getting a 1 penny coin and cutting it into 10 equal parts, and that's one of them would be 1 here, so 2 would represent this 2 there, but we haven't got that kind of coin to represent it nowadays. But the idea is that this is smaller than 10 times smaller than a penny. And 0.2, it means that we've got £0 and 20 pence. And what about this? So this would be £0 and 22 pence. So if I'm to order these, which one would I pick first? So let's say I want to order them from the biggest to the smallest. If I look at these, I have a pound there, whole pound, a whole pound there. I have 2 whole pounds there, £0, £0. So this must come first because pounds have a greater value. So, and that's 2 whole pounds. So I'm going to go 2.422. And then after this, which one would I pick? Then I would go for the one that has at least a pound. So, but these two, they both have a pound. This has 40 pence and this has 40 pence. This has 2 extra pennies, as you can see. This doesn't have any of those. So I'll go for 1.42 and then 1.4. And if I'm comparing them to, then this means 20 pence. So 0.2 means 20 pence, and this means 22 pence. So I'll go for the 22 pence first. So I've ordered them from the largest to the smallest. Now, one more question. If I'm to compare 0.2 with 0.02, which one would be bigger? As we said before, 0.2 is the same as 0.20. So in terms of money, this would be 20 pence. And whereas this is going to be 2 pence. Because if you remember the order, we'd have the 10p first and then the 1p after that. So there is no 10p coin here, but that 2 pennies in there. So the value of this is just 2 pence and this is 20 pence. So this must be bigger. So I hope this has helped you to read, write, order and compare decimals up to 3 decimal places. In this video we'll learn to add, subtract, multiply and divide decimals up to 2 decimal places. So I'll start with adding. If I have £2.35 and £4.80, I would add these starting from the right and making sure I've got them lined up so that the decimal points are lined up so that pounds are under the pounds, the 10p or the tenths are under each other, and the pennies or the hundreds are under each other. So that would be 5p, that would be 0, and that should be one under the other. So we get 5 and 0 makes 5, 3 and 8 is 11, so 1 down and 1 carried over. Put the decimal point in line with the other two, and we got 2, 3 and the 4 makes 7. So this would be £7.15 if it was money. But sometimes we might have to add different types of decimals. So let's say I want to add 10.3 with 1.45. Notice again the decimal is under the decimal, so that we've got the digits with the same value under each other. If you have no digit at the end there, then you could add a 0 because it doesn't make a difference. So 0 and 5 is 5, 3 and 4 is 7, 0 and 1 is 1, and there we go. So this is what these two add up to. So the thing to remember here was to line the numbers up so that we have the decimal points aligned. Then subtraction. So let's say I want to do 10.3 minus 4.56. So again, lined up. We have no digit here, so I can fill it with a 0. 6 taken away from the 0. We can't do so, we need to borrow 1 from the 3. So the 3 becomes a 2 and this becomes a 10. 10 take away 6 is 4. Now we need to take away 5 from the 2, which means we've got to borrow 1 from the 10 to make it 9. And this becomes 12, so 12 take away 5 is 7, 9 take away 4 is 5, so 5.74. And let's try another one. So if we have 4.03 take away 1.2. So again, there is no digit here, so I can fill it with a 0. 3 take away 0 is 3. 0 take away 2 would give a negative number, so I'll borrow 1 from the 4, so 3, this becomes 10. 10 take away 2 is 8. 3 take away 2, take away 1 is 2. So 2.83. So what is important is lining up the numbers so that we have the digits of the same value under each other. So the easiest way to do it is look at the decimal points. If they lined up, you're absolutely right. And then start working with them in the same way that you do with whole numbers. Now let's have a look at multiplication. So I'll try and multiply decimal numbers. So if we have 4.3 times 5.8. So what we do is that we completely disregard the decimal points to begin with. So I would go 8 times 3, which is 24. So I'll put 4 down and the 2 carried over. And I will then go 8 times 4 is 32 and the 2 is 34. So now I will multiply, put a 0 down, just like we do with whole numbers. 5 times 3 is 15, so 5 down and 1 carried over. 5 times 4 is 20 and the 1 is 21. Now add these up together. So we got 4 and 0, 4, 4 and 5, 9, 3 and 1, 4, 2. So there we have them. Now the final thing before moving on, it would be checking how many decimal places do the two numbers that we multiplied have. So the first one, 4.3, has 1 decimal place, meaning 1 digit after the decimal point. And the second number also has 1 decimal point. So I'm going to add them up. 1 decimal point there and another one here makes 2. So I'm going to give this number 2 decimal places. So we go 1, 2, and the decimal point goes right there. 24.94. And let's do another example. Let's say we've got 4.36 times 5.82. So 2 times 6 is 12. So 2 down and 1 carried over. 2 times 3 is 6 and the 1 7. 2 times 4 is 8. Now we're finished with this. Add 1 decimal point. We go 8 times 6 is 48. So I'll put 8 down and 4 carried over. 8 times 3 is 24 and the 4 is 28. So 8 and 2 carried over. 8 times 4 is 32 and the 2 34. Now we're moving down again. So now not just 1 0 we add, but we add 2 zeros. Because there are 2 digits after the 5, which we're going to multiply now. So 5 times 6 is 30. So 3 down and 3 carried over. 5 times 3 is 15. And the 3, 18. So 8 down and 1 carried over. 5 times 4 is 20 and the 1, 21. Now add them up. So we go 2, 7 and 8 is 15. So 5 down and 1 carried over. So I can have that here. 8 and 8 is 16 and the 1, 17. So 7 down and 1 carried over. 8 and 4 is 12 and the 1, 13. So 3 down and 1 carried over. 3 and 1, 4 and the 1, 5. And then 2. So where do I put the decimal point? Let's have a look. We have 1, 2 decimal places in the first number, 1, 2 decimal places in the second. So together there are 4. 2 and 2, 4. So I'm going to go 1, 2, 3, 4. So the decimal point will need to go between 5 and 3. So this becomes 25.3752. We'll now look at dividing decimals. So if we have 5.6 divided by 2. So we'll try and fit 2 into 5, and that fits twice, and there is 1 remaining. Now at this point where we finished with a digit and we've got a decimal point, that's when we transfer the decimal point to the answer as well. So I finished with a 5 and I transfer the 0 over there, the decimal point over there after the 2. Now I've got 16, so how many 2's fit into 16? And that is 8 of them. So the answer is 2.8. So we'll now look at another example. So if we have, let's say 5.64 divided by 4. So how many 4's would fit into 5? That is 1. So 1 is transferred, but don't forget we finished with a 5, so we'll transfer the decimal point to the answer. Now we've got 4's into 16, that is 4 of them, so nothing remaining, and then 4's into 4, there is just 1. So the answer is 1.41. Now another example. So if we got 4.8 divided by 1.2. Now this is a bit more complicated if you try and fit decimals into the number. So in this particular case, probably not as difficult because it's 1.2 and another 1.2 and another 1.2 and another 1.2. So 4 lots of them would make 4.8. But I want you to be familiar with a method so you can use it with more difficult to work with decimals. So if we've got 4.8, that's been divided by 1.2. We looked at fractions before, so we said that is the same as saying 4.8 over 1.2. So that line means division, and that's what we're doing. So that number is divided by that. So in order to get rid of the decimals, what I would do is I would multiply the top and the bottom number by 10, 100 or 1000, so that we make them into whole numbers. So to make this a whole number, I need to multiply by 10, so that a decimal point would come over here at the end. So to make this 48, I multiplied by 10. So I need to do the same with the denominator, so times 10. That means that 1.2 turns into 12. And what have we said about fractions? If we multiply the top and the bottom number by the same number, the fraction will remain the same. So we've got an equal fraction over here. 48 over 12 is the same as 4.8 over 1.2. So now it's a bit easier for me because I can say, okay, 48 divided by 12. How many 12s fit into 48? And that's exactly 4. So it's easy to work with the whole numbers. So turn them into fractions, multiply by 10, 100 or 1000, both of them, the top and the bottom number, and then just divide the whole numbers. In this video, we'll learn to approximate by rounding to a whole number or to 1 or 2 decimal places. We'll have a look at what that means in practice, but we round in daily life when it comes to shopping, so you kind of estimate given the amount, so you actually round in order to estimate. And this is what we're going to be doing now. So we're going to round to a whole number, to 1 decimal place and to 2 decimal places. To round to a whole number means to have your answer as just a whole number. No decimal point and no decimal places. So there we have 4.6. That means I just want an answer that is a whole number. So 4.6 is between 4 and 5. Which one is it closer to, 4 or 5? And that is actually closer to 5. And I can show that here. So 4 and 5, there is 4.5, 4.6 would be here. So that is closer to 5. And for that reason, we'll round it to 5. Round it to the nearest whole number, that is a 5. 15.4 is between 15 and 16, and that is 0.4, which means it's closer to 15. So the answer will actually be 15 to the nearest whole number. 416.48. So that is between 416 and 417. Now, if this was money, it would be £416 and 48 pence. 48 pence is closer to 416. So it's less than halfway through between 416 and 417. If it was 50 pence, then we would go up. So we're going to round down to have this as 416 to the nearest whole number. Now, to 1 decimal place, so we've got 7.48, we need to have just 1 decimal place, meaning that I need to cut off this decimal here. So I need to have just 7.4 or 7.5. So which one is this closer to? And of course it is closer to 7.5 because of the 8, and we've said is if it's 5, 6, 7, 8 or 9, then we round up. So this goes to 7.5. Now again, I need to cut this off here. So do I have 3.0 or 3.1? I'll go with 3.0 because 4 is rounding down, so means rounding down. So I can have this as 3.0 or just 3. Now 15.839. Again, I need to cut this off here because this is telling me 1 decimal place. So in order to decide, I'll look at the digit on the right, and that is the 3, and we've said if it's 0, 1, 2, 3 or 4, we round down. So we'll keep this as 15.8 rather than 15.9. Now to 2 decimal places, so we go cutting off here. So do I keep this as 16.43 or go to 16.44? Now the 2 next to it, next to the 3, tells me that we've got to round down. So we're going to keep this as 16.43. Again, 1, 2, so cut off here. The 9 tells me whether I keep this as 0 or round it up to make it a 1. So 9 is one of the high numbers, which means we need to round up. So this becomes a 1. So I have now 19.91. And again, here I need to cut this off here. So we go 19.99. And this tells me I need to round up. So this is a 9, it becomes 10. But as we've talked about this before, it means we need to transfer 1 over here and then 1 over there. So this now, rounded to 2 decimal places, becomes 20 or 20.00 if you like. So now, final example, we've got 10.508, which I'll round to the nearest whole number, to 1 decimal place and 2 decimal places. So to the nearest whole number, this is actually 10.508, so I will keep it as 10 or go to 11 is the question. And to decide that, so here is the cutoff point. I look on the right, so this is a 5, meaning that I need to round up. So this is actually more than 50 pence if it was money. So I would round this to 11, to the nearest whole number. To 1 decimal place, meaning I need to have just 1 digit here after the decimal point. So I'm gonna either have 10.5 or 10.6. Looking at the digit next to the 5 where I need to cut it off, it's a 0, meaning that I need to round down. So this is going to stay as a 5. So I'll have 10.5. To 2 decimal places, meaning that I need to cut this off here. So I'll look on the right, we've got an 8, meaning that I need to round up. So this becomes a 1. So we have 10.51. So I hope this has shown you how to approximate by rounding to a whole number to 1 decimal place or 2 decimal places. In this video we'll learn to read, write, order and compare percentages in whole numbers. So first of all, I'll start by asking, what does a percentage mean? What does that percent means? Percent means out of 100. So 18% means 18 out of 100. 4% means 4 out of 100. 39% means 39 out of 100. 40% means 40 out of 100. And 83% means 83 out of 100. And I'll add a final one, let's say 150% means 150 out of 100. Now, if this is how I write them, 18%, 4%, 39%, and that's how we read them as well. So 40%, that's the percentage symbol with a slash and the 2 circles. 83%, 150%. And if I am to order and compare them, it's pretty straightforward. It's just like comparing numbers. So if I look at these, the highest amount is 150. So 150% would be the highest percentage here, because it means not just 100%, but another 50%, another half. And then 83% would be the next biggest one, because 83 is the next biggest number. And then we'd have 40%, 39%, 18%, and 4% finally. So this is how to compare them, and this is how to write them and read them. In this video, we'll learn to calculate percentages of quantities, including simple percentage increases and decreases by 5% and multiples thereof. We use percentages and we work out percentages in our everyday lives. Maybe when it comes to sales, price increase, price decrease, but maybe we're not aware that we're doing it. So what we'll focus in this video is on how to work out 10%, 5%, 15%, and then increases by these amounts. So the amount that I've picked is 500. This could be 500 pounds, 500 meters, 500 liters. So it could be anything really. It's a quantity. I will work out 10% of 500 first. So as you can see, there is a bar next to 500. So this whole bar represents 500. We have 0 here and 500 here. So I want to find 10% of this. I've intentionally split this bar into 10 equal parts. So if this whole bar is equal to 100%, the total amount, how many percent will be represented by each of these divisions, by each of these parts? So there are 10 of them, so that means that there will be 10% in each of these. So I got 10, 20, 30, 40, 50, 60, 70, 80, 90, 100%. So this is equal to 10%. Now, this represents 10% of the bar, but also 10% of the amount. So this is 500, 10% will be a tenth of 500. So I need to divide the 500 by 10 as well, just like I did with the bar. So 100 divided by 10 give me 10. 500 divided by 10 gives me 50. So that means that I'd have 50 here. 10%, 20%, 30, 40, 50, 60, 70, 80, 90%. So this will go 50, 100, 150, and so on. So that's the same pattern, adding 50 each time. But I don't need to continue this, because all I need is to work out 10% of 500, and I've worked that out, which is 50. So what I did was divided 500 by 10. Now I'll work out 5% of 500. If we look at the next bar, so this is 10%. 5%, what part of 10 is 5? It is actually half of it. So I'll need to cut 10 into 2 equal parts. So this would be 5%. So it's half of the 10. And if 10% was equal to 50, then 5% must be half of it, which is 25. So by having 10% already, all I did is half the 50 and get 25. So 5% of 500 is 25. How about 15%? Let's have a look at the bar. Where is that positioned? So here is 10%, there is 20. 15 must be between 10 and 20, so it's got to be here, right in the middle, between 10 and 20. So this is 15. Now we said 10% was 50 and 5% was 25. So all together, the 10 and the 5 makes 15. So the 50 and the 25 makes 75. So at this point, I'd have 75. So 15% of 500 is 75. So if you wanted to work out, let's say 1% of 500, then compare it to this. That's 10%, so 1% is going to be 10 times smaller. So I can pick that 50, divide by 10, and it gives me a 5. Or I could go, how many 1% fit in a 100%? And that is 100 of them. So I must divide 500 by 100, which gives me 5 again. So that's another way of working it out. And let's say I want to work out 16%. So 1% was 5, 15% is 75. So to find 16%, I add 15 and the 1, so 75, and the 5 gives me 80. I will also show you a calculator method to work this out. So 10% we've said means 10 out of 100, because percent means out of 100. So 10% I'll write as 10. So 10 out of, or divided by 100, because it means the same thing, equals 1/10 or 0.1. And we know that because it's like money. 10% is like 10 pence in a pound. And that's how I would write 10 pence in a pound. So there, I've got it. Then times 500, the whole amount, times 500. And that gives me 50. Let's do the same here. So 5 out of 100, that is 0.05, again like 5 pence, times 500, because off means times. So that is 25, which is the answer we had. And let's say 15%, so 15 out of 100 times 500, that gives me 75. So I can work out any amount really. Let's say 17%, so 17 out of 100 times by 500, so that gave me 85, which is 17% of 500. So the shorter way to work it out would be, so that's 10%, which I can write as 0.1 times 500, that gives me 50. And the same thing, 5%, like 5 pence, are at 0.05 times 500, that gives me 25. And 15% I write as a decimal, write at 0.15 times 500, that gives me 75. We'll now look at decrease. So if I wanted to decrease 500 by 10%, what would happen? So we've got the 100%, that's 10%, so it's going down by 10%, so we only have the remainder, whatever there is remaining. So how do I work it out? Since it's a decrease and going down by 10%, that means 500 is going down by 50. That means whatever is remaining, which is 450. So that is the new amount after the 10% decrease. So it's the 90% that's remaining. And if we look at a decrease of 500 by 5%, that means we're taking away 25 from it. So that is 475. So that 475 makes 95%, whatever is left after the 5%. And if we decrease 500 by 15%, so that is going to be 425. So that makes 85%. So work out what you're decreasing by and take it away from the full amount. Another way to work it out is to look at, okay, so we're decreasing by 10%. So what is left from the 100%? That's 90%. So 90% I do as 90 over 100, or 0.9 times 500, which is the full amount. That gives me 450 again. Or here, if we take away 5%, what we're left with is 95%. So I'll write that as 0.95, just like 95 pence in a pound, times by 500. That gives me 475. And if I take away 15%, I'm left with 85. So I write that as 0.85 times 500. That gives us again 425. So we can work out any new price given the decrease by just taking away the percentage of the decrease from the 100%, turning it into a decimal and multiplying by the full amount. Now look at increase. So what increase means is the amount will go up. So if I want to increase 500 by 10%, that means I've got the 100% already, and I'm going to add 10% on top. So one of these rectangles, so that 10% that I add here, I'm going to add it on top. So this is already in place, and there is an extra 10% on top. And we said 10% was 50. So that means I'm going to add that 50 on top of the 500. So that will become now 550. So 500 was the original amount, added the 10%, which was 50, that made 550. And if I look at an increase of 5%, that means I've got the 500 already, and I'm adding 5% on top. And we said 5% was equal to 25. So there is the 500, I'm going to add the 25. So that's going to make 525. And if I now look at 15%, so I'm going to add 10% and the 5%. So altogether that was 75. So that's going to be on top of the 500 to make 575. And if we look at the calculator method, now pay attention, that was 100%, now we added 10%, so that became 110%. 110%, we say 110 divided by 100, or out of 100, so that gives us 1.1. So 1 is already a whole 1, and adding 10%, which is 0.1, so that makes 1.1, times the 500, which is the 100% of the original amount, that makes 550. And here we have 100 and we added 5%, so that made 105. Now 105 pence, if you had, that would be 1.05, or 105 divided by 100. Now multiply that by the full amount, which was 500, that gives us 525, which is the same answer that we had before. And 100 add 15, that makes 115%. So 115 pence out of 100, that would be 1.15 times the full amount, 500. That gives us 575, which is what we worked out before as well. In this video, we'll learn to estimate answers to calculations using fractions and decimals. So we've got a couple of questions here with fractions and decimals. And estimating again means using a rounded figure, not the actual figure. So that is really important. So looking at the first question, I've got 3/16 times 7/13. Now if I just went on and multiplied the top numbers and the bottom numbers as they are, I'd get the answer wrong, because I'd get the actual answer, and I'm looking for an estimate. So it's an estimated answer that I'm after. So what I'm going to do, I'll look at the numbers, and it is 3 out of 16. So I know that if I split 16 into 4 equal parts, or I get a quarter of it, I'd have 4. So 4 out of 16 is 1/4. And 4 is very close to the 3, so 3 is close to the 4. That means that this is about 1/4. And 7 out of 13, double 7 is 14, so it does look like it's close to a half, because 7 is half of 14. So that will be times a half. So this is then 1 times 1 is 1, and 4 times 2 is 8. So this is about 1/8, estimating the answer to this question. And again, I'm going to estimate the answer to this other question. So we've got 3 out of 16, as we said before, so that is close to a quarter. So it's the same as saying finding a quarter of 20. So what is a quarter of 20? Half in 20 first, that gives us 10. Half again, that gives us 5. So a quarter of 20 is 5. And with decimals, we've got 0.45 times 150. Now, I know that that is very close to half, which is 0.5. So I'm going to use that rounded figure to multiply by 150. So half of 150 really, which is 75. So this is about 75. And 0.45 of 70, that is again 0.5, we round it to, so this is about 35. So when it comes to estimating, as we said, we round the figures, we're looking at what they're closer to. Sometimes we have to simplify, sometimes we have to scale up, like we did here. That was 16, so if I divided it by 4, that would give us 4, so that gave me the suggestion that this is about a quarter. And this one here, again, half, or doubling that. So either multiplying both of the numbers or one of the numbers to see what's the relationship of that with the next one, so you get an approximate figure. So this is how you estimate answers to calculations using fractions and decimals. In this video, we'll learn to recognize and calculate equivalencies between common fractions, percentages and decimals. So I've got a bar here which has been cut into equal parts. That represents from 0 to 100%, or the whole, or 0 to a whole as well. So it means the same thing. What we're using at the top is decimals, at the bottom is percentages. So we'll try and use fractions, decimals and percentages to find the equivalent versions of them. So let's have a look first at this amount. So up to this amount, which is here, what would that be as a fraction? As a fraction, this will be 1 out of the 10, or 1/10, because there are 10 overall and this is just one of them. Now, what is that equal to as a decimal? So if I am to put a decimal there, what would that be? That is the same as saying 1 divided by 10, or 1 out of 10, and we should know that 1 out of 10 means 0.1. So I'd go 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and then 1. So this is the same as 0.1. And 0.1, 1 out of 10, or 0.1, is the same as 10%. I always relate this to pence. So if you see this amount, it would mean 10 pence. And that links with percentage. So they both start with P. So with a calculator, I would do 1 divided by 10. So that gives me 1/10. As a decimal, that's 0.1. And that is 10% as well. So if you multiply it by 100, as that's another way, that gives you 10%. Now let's have a look at this one here. So this is going to be 2 out of 10, and it's going to be 0.2 and also 20%. So you can see the pattern. This would be 3 out of 10. That would be 0.3, 30%. This would be 4 out of 10, 40%, or 0.4. This would be 5 out of 10, or half. So half is 1 out of 2, which write as 0.5, and that is 50% as well. And this would be 6 out of 10, which is 0.6, or 60%. This would be 70%, 7 out of 10, or 0.7. And this one would be 75%. It is 75 out of 100. It is 0.75, and it is also 3/4, so 3 out of 4. And if you do this with the calculator as well, 3 divided by 4, that gives us 3/4, which is 0.75. And that is 75% as well. So this one here would be 8 out of 10, which is 80%, or 0.8. This would be 90%, which is 9 out of 10, or 90%. This is 95%, 0.95, and it is 95 out of 100 as well. And this one here is 5%, which is the same as saying 5 out of 100, or 1 out of 20. And we write that 0.05. Another common fraction is 1/8, so 1 out of 8. And if you use a calculator, 1 divided by 8, that gives us 0.125, which is the same as 12.5%. If you want to work this out in your head, then you'd probably cut this into 4 equal parts first, which means you get quarters, which is 0.25, and then cut those into halves again, so that gives you 0.125, which is 12.5%. So the way to turn any fraction really into a decimal and then percentage, you'd be write the fraction. So let's suppose it's 2/7 or 2/7, and you divide 2 by 7 either by hand or in your head or using a calculator. So 2 divided by 7, that gives me this decimal, which is 0.29. I'll round it up. So 0.29. Now as a percentage, that would be 29%. So any fraction, divide the top by the bottom, turn it into a decimal, and then you can see clearly it's like pence in a pound, or multiply by 100 and it will give you the percentage. In this video, we'll learn to work with simple ratio and direct proportions. We use ratio when it comes to mixing drinks together. That's just one example. So I'll use that example to illustrate. So I've got a drink here which requires mixing. So I look at instructions to see how many parts of the drink with how many parts of water I need to mix. So if I look at the instructions, it says dilute 1 part squash with at least 4 parts water. So I would have 1 part squash with 4 parts water. So these are supposed to be equal shapes. Because I need to use the same amounts. So what I've used to measure is just a scoop. You could use anything that you want, so that I can fill this with a drink. So I'll have 1 part juice and 4 parts water added to it. So there is 1 part of the juice. Now I'll put in the 4 parts water. 1, 2, 3, 4. So this is how the drink looks like when it's measured correctly. And as you will have noticed, I used the same scoop to measure both the juice and the water. Why have I done that? Because if I used different containers, different scoops, I would perhaps have a different ratio. Actually, I will definitely have a different ratio. It won't be the same. So if you look at it now, there is 1 part juice with 4 parts water. And if I use different containers, then they wouldn't be like for like. So I wouldn't have the same drink. So this is the ratio 1:4. So the ratio of drink to water is 1:4. That's how we read it. Now we'll actually try and see what would happen to the drink if we mixed more parts of juice than we actually asked to. So I will change this to 2 parts juice and 3 parts water. So again, in total I'll have 5 parts. I'm not changing the amount of drink that I'm making. So let's have a look. So I'll put in 2 scoops of juice. 1. There is 2. And we'll need to mix it with 3 parts water. 1, 2, 3. So this is the ratio 2 to 3, the ratio of juice to water. I don't know if it's very clear on the camera, but this drink is darker than that one because we've got more juice in. Maybe we can try and compare them this way. So this is getting darker. What would happen if I mixed 3 parts juice with 2 parts water? So 2 parts water now. So this is even darker. So that is 2, 3 parts juice and 2 parts water. So this is the 1 to 4 ratio, this is the 2 to 3 ratio, and this is the 3 to 2 ratio. We're talking about the ratio of juice to water. And the drink gets darker and darker because there is more juice in it, so it's more concentrated. So if we mixed 4 parts juice with 1 part water, it will be even darker. We'll focus now on the ratio of juice to water, 1 to 4, because that's the one that we should be using for this drink. So if you notice, for 1 part of juice, you need to mix it with 3 more parts of water. So not just 1, but 4 parts altogether. Or in other ways, you mix in 4 times of juice. So the amount of water is 4 times the amount of juice. And this is how we write that. 1 to 4. So 1 is juice and 4 is water. it's important to label them, because then you'd get mixed up which one is juice and which one is water. Although when we say it, that's what tells us the order. So I said the ratio of juice to water. So I'll say whatever comes first, the ingredient that comes first, I would say that first. And that's what you read in the questions as well. So it will be the same order in the questions. So we'll try and see what actually happens if I wanted to make 2 cups of drink. If I wanted to double the amount of drink, what would happen? So here I have my cup, and I'm going to make another drink of the same ratio. So I will make ready 1 part or 1 scoop of juice. That's in. Now I need 3 parts of water, so the ratio remains the same, because it's really important if we want to get the juice right. So I will go 1, 2, 3, 4. So the ratio is the same, it's the same type of drink. And so what did we do? How much did I put all together? How much of each of the ingredients? How much juice and how much water? So I actually mixed again 1 part juice and 4 parts water. So the ratio is the same. Now in total for the 2 cups, how much juice did I put in? I put 1 there and another here. So I put 2 parts juice, and how much water in total? That was 4 and another 4. That made 8 parts water. So what do we notice? I'm making double the amount of juice. So I'm actually now having 10 parts in total. So I'm doubling the amount. I'm having 2 cups now. What's happened to the amount of juice? It's gone from 1 to 2. So it's doubled. Multiplied by 2. What's happened to the amount of water? It's doubled as well, so it's been multiplied by 2. So if I want to make another cup of drink, there we go. I'll need to mix again for that drink 1 part juice and 4 parts water. 1, 2, 3, 4 parts water. So for the 3 drinks, what do I have? I have now in total, I have 1, 2, 3 parts juice, and I have 4, 8, 12 parts water. So what happened? I made 3 cups, so the amount of juice was multiplied by 3. So 1 times 3 gives me 3. And the amount of water was multiplied by 3 as well. So 4 times 3 gives me 12. So what we're learning through this is that whatever you multiply one amount by, you need to multiply the other one by as well in order to keep the ratio the same. And what we call this ratio staying the same as you increase the amounts, we're saying these amounts are increasing in proportion. We call this direct proportion. So if you double one amount, you double the other one. If you treble one amount, you treble the other one. So this is what happens. Now I want us to think. I have 4 parts of juice available. how much water do I need to mix that with so that this goes in proportion, so we don't change the ratio. Now, if I look at this, to get from 1 to 4, I've multiplied by 4. So I must multiply by 4 the amount of water as well. So then we got 4 times 4 gives 16. So 16 parts of water I mixed with 4 parts of juice. So if I have 32 parts of water available and I want to know how much juice I'll need to mix with that amount of water, so I'll need to find out what's happened. How did we get from 4 to 32? What did we multiply it by? And that was by 8, because 4 times 8 gives me 32. So I must multiply 1 by 8 as well, so that the ratio remains the same. So that 1 times 8 gives me 8. So 8 parts of juice will be mixed up with 32 parts of water. Another thing I would like us to look at is the total. What happens to the total amount of juice? So when I made one drink, I mixed 1 part juice with 4 parts water. So that was in total 5 parts that made the drink. Now, when I doubled the amount, so I made 2 drinks, all together I had 2 parts juice and 8 parts water. So both that made 10 parts. So I doubled the amount, and that 2 and 8 gives me 10. So what do you notice between 5 and 10 as well? That doubled as well. So it multiplied by 2. 5 was multiplied by 2. So 1 times 2 gave us 2. 4 times 2 gave us 8. And 5, which is the total, times 2 gives us 10. So let's see whether that's the case with this. 3 and 12 gives me 15. So what's happened from the 5 to the 15? What have we multiplied by? It's by 3, which is exactly what we did with each of these ingredients. So juice, 1 times 3 give us 3, and water, 4 times 3 give us 12. So we multiply the total as well by the same number. And let's look at that. We've got 4 and 16 makes 20. So 1 times 4 gives us 4, 4 times 4 gives us 16, and 5 times 4 gives us 20. So the total has been multiplied by 4 as well. And 8 and 32 gives us 40. So 1 times 8 gives us 8, 4 times 8 gives us 32, and 5 times 8 gives us 40. So it is exactly the same number you're multiplying each ingredient by, as well as the total. So my question is now, if you wanted to make 100 milliliters of drink, all together 100 milliliters of drink, so the total would be 100 milliliters. What amount of juice and what amount of water do you need to mix? How many parts of juice and how many parts of water? So I'll look at the total. So I need 100, and the total for the ratio that we started with, 1 to 4, was 5. So what do I do to 5 to get to 100? That is multiplying by 20. So I've got to do the same with these ingredients. So I'll go and multiply the juice by 20 to give me 20. So 1 times 20 is 20. And the water, which is 4, times the 20 gives me 80. So I multiplied by the same number. And that was 100 milliliters. So these must be milliliters as well, because they haven't got any units. So that suggests that the units will be the same for all the ingredients and the total. So let's recap some of the key things, what we learned. So the ratio is written as 1 to 4. So a number with 2 dots and a 4, and is read as 1, 2, 4. 2 to 8, 20 to 80, and so on. What we learned is that we've got to keep the amounts the same. So if you're using 1 unit, so the container you're using to measure the juice, you need to use the same container to measure the water to keep the amounts the same. Otherwise the ratio wouldn't be the same. What we learned also is that if we increase the number of units of one of the ingredients and decrease the other one, then the juice will change. It won't be the same. Ours got darker and darker as we added more of the juice, and we decreased the amount of water. What we also learned was that if we double the amount of one ingredient, we have to double the amount of the other ingredient. If we treble the amount of one ingredient, we'll treble the amount of the other one. If we multiply by 10 the amount of one ingredient, we'll do the same for the other one. But what we also learned is that whatever you multiply the ingredient by, you have to multiply the total by as well, because even the total increases in proportion. In this video, we'll learn to calculate simple interest in multiples of 5% on amounts of money. So we'll look before at percentage increase and decrease, and this is really connected to increase, simple interest. Simple interest is what you paid when you invest some money in a bank, for example. So they pay you some money in return for having or for saving your money. So when we have a 10% simple interest rate, a 10% interest rate, what that means is that you are being paid 10% on your investment year on year. So at the end of the first year, you'd be paid 10% of that amount. So if you invested £500, then that means that at the end of year 1, you'd be paid 10% extra. So at the end of year 1, you'd have £550, because £50 is 10% of 500. So at the end of year 1, you'd have 550. Then the next year you're given another 50, so another 10%. So this continues to expand. So another 10% and another 10% and so on. So add another 50, that makes 600. So at the end of year 2, you'd have £600. At the end of year 3, you'd have 650. At the end of year 4, you'd have 700, and so on. So adding £50 each year. That's what it means when you paid 10% simple interest. 5% then again, so 5% we said was 25. So at the end of year 1, you'd have 525. And then add another 25, that's 550 at the end of second year. 575 at the end of the third year, and 600 at the end of the fourth year, and so on. So adding £25 year on year. And if the interest rate is 15%, you'd be having 15% on top of that, of the 500 at the end of year 1, so which is 75. 15% of 500 is 75. So that means at the end of year 1 you'd have 575. At the end of year 2 you'd have 650. At the end of year 3 you would have 725. At the end of year 4 you'd have 800, and so on. So adding on £75 or 15% each time. So what this means, simple interest, is adding the same percentage, the same amount year on year. In this video, we'll learn to calculate discounts in multiples of 5 on amounts of money. So discounts are the ones that are applied on when you purchase different items which are on sale, and this links to decrease, which we've looked at in another video on increase and decrease. So if you need to refresh your memory, go back to that video. Now, what does this mean, discounts? So the original amount is being reduced by a percentage, and we'll look at 5%. So if the original amount of a coat maybe is £500 and there is a discount by 10%, that means that 10% is reduced from the original amount. So, and we worked out 10% before of 500, which was £50. So I'll take that away from the 500 to give me £450. And if the discount is just 5%, then we take away 5% from the £500 to give us £475. And if the discount is 15%, so 15% of 500 is 75, taken away from the 500, that gives us 425. So really, discount is decrease. In this video, we'll learn to convert between units of length, weight, capacity, money and time in the same system. If you've forgotten or get mixed up with main facts about length, weight and capacity, such as how many centimeters in a meter, how many millimeters in a centimeter, and so on, go and check the entry 2 and entry 3 videos on measurement, because that's the starting point when you convert. So what I want to do now is convert between meters and centimeters. My question is, how many meters is 400 centimeters equal to? So the first thing I need to do is write the main fact about conversion between centimeters and meters, which is that there are 100 centimeters in 1 meter. Notice how I've written them in a ratio style, because I find that easier to make that connection, and we'll see what that means. So I've got the units labelled. I've got centimeters, I've got meters, 100 centimeters in 1 meter. You could have the units next to the numbers as well, so we'll try and do that, or change this to equals. So now I want to convert 400 centimeters into meters. So which one do I know? I know how many centimeters I have. So 400 centimeters this is. And we'll convert that into meters. Now I'll look at how many hundreds fit into 400, and that is 4 of them. So I've multiplied 100 by 4 to get 400. So I'll do the same with the meters. So I'll multiply 1 by 4 to get 4. So 400 centimeters is equal to 4 meters. Now we'll try another one where we convert centimeters to millimeters. So again, I need to recap. How many millimeters in a centimeter? And there are 10 millimeters in 1 centimeter. I need to find out 5.5 centimeters. How many millimeters is that equal to? So I know the centimeters, so I'm going to write them here. 5.5 centimeters, and I'll find how many millimeters that is equal to. So to get to 5.5, what do I do to 1? I multiply it by 5.5, because a number multiplied by 1 gives the number itself. That's the answer. But if I ever forget, I'll do the reverse. I will divide because the multiplication and division are the opposites of each other. So I'll do 5.5 divided by 1, and that would give me 5.5. So I'll multiply by the same number the millimeters. So multiplied by 5.5. So 10 multiplied by 5.5 gives us 55 millimeters. So 5.5 centimeters is equal to 55 millimeters. And now try and convert between kilometers and meters. So first of all, I know that in 1 kilometer there are 1000 meters. So now I need to find out 4.4 kilometers. What's that in meters? So again, what do I do to 1 to get 4.4? I multiply it by 4.4. So I must do the same with the meters. So I'm going to multiply them by 4.4. I will write this here, so times 4.4. So that gives me 4,400, because if you remember, when we multiply by 1,000, we move the decimal point 3 places in the positive direction to the right. So we go 1, 2, 3. So that is, the unit now is meters. So because it's the same on the same side, kilometers and then meters. So this shows you how to convert between units of length within the metric system. We'll now look at weight. So I will try and convert between grams and kilograms. I want to find out how many kilograms is equal to 1,150 grams. So first of all, the main fact. 1 kilogram is equal to 1,000 grams. So what do I know? I know that I've got 1,150 grams on the same side with the grams that we've got on the top. So how many kilograms is that equal to? So again, I'll try and find what's happened from 1,000 to get to 1,150. So I'm thinking, what is that number I've multiplied by 1,000 to give me 1,150? And that number is 1.15. If you're not sure, if you can't do this in your head, get your calculator out and go 1,150 divided by 1,000, which you also can do without a calculator at this point. So I'm going to do the same on the other side. I'm going to multiply 1 by 1.15. So that is exactly 1.15. So 1,150 grams is equal to 1.15 kilograms, or 1 kilogram and 150 grams. We'll now look at capacity. So I will convert between liters and milliliters. So I've got the main fact, which is 1 liter is equal to 1,000 milliliters. And I want to convert 0.8 liters to milliliters. So what is that equal to? So to get from 1 to 0.8, we've just multiplied it by 0.8. So we'll do the same on the other side. So we'll multiply 1000 by 0.8, and we've learned that we would move 3 places in the positive direction. So go 1, 2, 3, so that gives us 800 milliliters. So as you can notice, when it comes to length, weight and capacity, it's easy to work with in the metric system because it's multiplying and dividing by 10, 100 and 1000, and working with ones as well. So any number when you multiply by 1 gives you that number itself, and we've learned how to multiply and divide by 10, 100 and 1000. So most of these things you should be able to do even without a calculator. Now look at money and time. We know that £1 is equal to 100 pence. So if I want to find out that how many pounds make 780 pence, so I've got it on the pence. So what happens to get from 100 to 780, what do we multiply by? And that is 7.8, which is the same as going 780 divided by 100, so that gives us 7.8. So I'll multiply 1 by 7.8 as well, so that gives me 7.8. And don't forget that money is not written with 1 decimal point, so we'd write it fully as £7.80, not 7.8 pounds. So money was very similar as well to length, weight and capacity because we worked with 100 in there. Whereas in time, when it comes to time, we know that it's slightly different. We've got 60 seconds in 1 minute. So it's not 100. And we've got 60 minutes in 1 hour as well. So the method will be the same. So let's say we want to convert 8.3 minutes to seconds. What would we do? So to get from 1 to 8.3, we multiply by 8.3. So we'll do the same. So 60 multiplied by 8.3. So you should be able to do this either with a calculator or without a calculator. So that when we multiply now, it gives us 498 seconds. So 8.3 minutes is equal to 498 seconds. So let's suppose we were given 498 seconds and we needed to convert them into minutes, then 498 divided by 60 gives us 8.3. So that gives us what we're multiplying by. So I'd go 1 times 8.3 gives me 8.3. So it's the same thing, and exactly the same way of working out would be applicable if you convert it between minutes and hours, because there are 60 minutes in 1 hour. So it'd be the same answer if we had different labels. If you had here 1 hour and there 60 minutes. In this video, we'll learn to recognize and make use of simple scales on maps and drawings. I've got a map which I've printed off the internet, and what I would like to do is use this to work out the straight line distance between different cities. And the scale at the bottom says 1 centimetre represents approximately 30 miles. So that is the scale or the ratio. That tells us that 1 centimetre on the map is in actual fact 30 miles. That's the real distance between the places. So I will do the scale here. I'll write the scale. So we've got centimeters to miles. So 1 centimeter is approximately 30 miles. So I will start off by finding the straight line distance between Birmingham and Manchester. So I've drawn a straight line between the two cities, and I'll now measure using a ruler. What is the distance on the map? So starting from 0, this is 2.5. This ideally would be on the board when I'm bringing this closer to the camera so you can see it clearly. So it is 2.5. So that is 2.5 centimeters on the map. And we'll convert that to the miles in real life. So we'll look at how many ones fit into 2.5, and that is 2.5. So 1 times 2.5 gives us 2.5. So we'll do the same on the other side. So 30 times 2.5. What does that equal to? Now you can use a calculator to work this out. You can use any other method as well, or you can use a mental method. So written or mental. I'll use the mental one. So I'll break this 30 into 3 times 10. So 2.5 times 10 gives me 25. 25 times 3 gives me 75. So that is 75 miles. So the distance in reality, approximately, in straight line between Birmingham and Manchester is 75 miles. Now we'll look at another question using the same map. The distance between London and Cardiff in real life is approximately 144 miles. So again, it's the same ratio or scale. So centimeters, miles, we've got 1 centimeter, approximately 30 miles. So what we said was that the distance between London and Cardiff was 144 miles. So where does that go? That goes under miles. So we've got 144. Now we'll find out how many centimeters that is. So we'll look at them. What's happened to 30 to get to 144? So what did I multiply 30 by to get to 144? And how do I find that out? So I got 144 divided by 30. That should give me here 4.8. So I've multiplied 30 by 4.8 to give, or to get 144. So I'm going to do the same to 1. So times 4.8, that gives me 4.8 centimeters. So 144 miles in reality is approximately 4.8 centimeters on the map. So we found that the distance on the map is 4.8. So let's see whether that's the case. So we'll draw a straight line between London and Cardiff, and we'll measure it. So we'll go that is 4.8 approximately. So this has shown you how to recognize the scales, which are normally at the bottom of the map, sometimes at the top. So those numbers will tell you something. So this scale at the bottom, you might have it written here at the top as 1 to 30. So maybe 1 centimeter, 30 miles. and it means exactly the same thing. So look out for the units as well. If they have no units, that means you can use whatever unit you like, and you need to keep it the same. So if this was just 1 to 30, the scale was just 1 to 30, that would mean that 1 centimeter on the map is 30 centimeters on the scale in real life, the actual distance. If you use meters to measure, which is very unlikely in a map, but if you have a very big map perhaps, so that if that is 1 meter, that's going to be 30 meters in real life. So you keep the unit the same. Whatever you're measuring it on the map, that's what the unit will be in the actual distance. So we'll now look at a drawing. So I'll show you a drawing of a room. So it's like a map of the room, a plan of the room to be more accurate. So this is the length of it. Is it 8.4 in fact? So we'll go 8.4, and the width is 6.8. We'll show it approximately on the board. So that is 8.4 as well. So this was 8.4 centimeters and the width was 6.8 centimeters. The actual scale is 1 centimeter on the plan is equal to 50 centimeters in the room in reality. So how many centimeters is the length and the width of the room in reality? How do I do that? How do I work it out? So let's have a look at the length. We're saying, so this is the plan and this is real life. So we go looking at the length, it's 8.4 centimeters in the plan. So 8.4. In reality, what will that be? So to get from 1 to 8.4, we multiplied by 8.4. So we'll do the same with the 50, multiplying by 8.4. So 8.4 multiplied by 50, that gives us 420 centimeters. So in actual fact, the room is 420 centimeters long. So what is the width? So the width, again, we got 6.8 on the plan. What do we do to get from 1 to 6.8? We multiply by 8.4, so we'll do the same to 50. So 50 times 8.4, and that gives us 50 times 6.8, 50 times 6.8, because we worked out 50 times 8.4 already. So 50 times 6.8, 340 40 centimeters. So this was the width. So we'll now look at another question. So we've got another place, we've got another room. So there we have plan and real life, and the scale is 1 to 200. So the scale is 1 to 200. So that means that the units will be the same if you haven't got the units. Now in real life, this is 800 centimeters. The length of the room is 800 centimeters. So we'll need to draw it. So that's in real life, which is 800 centimeters. So what have we done to get from 200 to 800? We've multiplied it by 4. So we'll do the same thing over here. So times 4, that gives us 4 centimeters. So I'll draw that using a ruler on the centimeter side. So we start from 0, we go up to 4, so that's the length, and the width is 550 centimeters in real life. What will it be on the map? So let's have a look. 550, that comes under the real life, and it's 550 centimeters, so our answer will be in centimeters as well. To get to 550 from the 200, what have we done? So what have we multiplied by? So I'll do the reverse. 550 divided by 200, and that gives me 2.75. So I've multiplied by 2.75. So I will now multiply 2.75 by 1, or 1 by 2.75, which is 2.75 centimeters. So I will draw that as the width. So 2.75, so 2 3/4 on the other side as well. 2.75. You're often given graph paper or squared paper to draw these in, because it's easier to do that. So that's the length and that's the width. So the important thing was to write the scale or the ratio first, and then find out the information you're given. Is it the one on the map or on the drawing, or is it the one in real life? And put it on the right side. Like here we've got the plan, so everything revolving around the plan will be on the same side, and the real life will be on the same side as well. The other thing to look at is the units. If the scale doesn't have the units, you give it the units that you want. So if you're measuring in centimeters, that's what it will be throughout. Both sides will be in centimeters. In this video, we'll learn to calculate the area and perimeter of simple shapes, including those that are made of a combination of rectangles, like these ones here, which I call the compound shapes. We'll start with the perimeter. And what is the perimeter? The perimeter is measuring the length around the shape. So I'll go around and measure all of these and add them up. So let's suppose this is the plan of a room, and I'd want to put the skirting board around the room. So what I'll do, I'd measure these lengths, add them up and work out how much skirting board I would need. A clue is within the word perimeter, rim, the rim of the room, going around. So we'll look at working out the perimeter of all these shapes. So we've got some squares here, 2 squares. This length is 7 centimeters. So the other side must be 7 centimeters as well. And this must be 7 centimeters as well, and this one. The reason being because it's a square and all sides are equal. So we've got 7 and 7 and 7 and 7. So that's a way to work it out. So adding 7 plus 7 plus 7 plus 7. So 4 lots of 7, which is 28. What unit are we using? That's centimeters, so that's what we get out, 28 centimeters. Now we've got another square here, and each side is 4 meters. So 4 times 4, because there are 4 sides, and 4 meters each. So that means we can write it as 4 times 4, or 4 plus 4 plus 4 plus 4, and that gives us 16 meters. Why is it meters? Because we input in meters. So 4 meters and another 4 meters, that's 8 meters. Another 4 is 12, and another 4 is 16. So 16 meters, and we're going around. Now, rooms or other objects might have a shape like a rectangle. So they might be rectangular. So we'll try and work the perimeter of this first rectangle. We can see the length, which is 8 meters. And because this is 8 meters, so must this side be as well. So that is 8 meters as well. This is 3, so this must be 3. We know this because it's a rectangle. So what do? I add these, go round and add all of these, and work out the total. So 8 and 3 and 8 and 3. So 8 and 3 is 11, and another 11 is 22. 22 meters. I cross these out to make sure I don't miss out any of them. And the same thing over here. We've got 4, so this must be 4 centimeters this time. 6 centimeters and 6 centimeters. So I'll go and add them. 4 plus 6 plus 4 plus 6. So 6 and 4 makes 10, and another 10 makes 20, so 20 centimeters. Other people might add 4 and 4 first, and then 6 and 6, and add both the totals together. Both ways are perfectly fine. Now, looking at compound shapes. So compound shapes are shapes which are made of 2 or more smaller shapes. In this case, these are made of rectangles and squares. So what I'm going to do is, again, because perimeter means going around, so I'll go around the whole shape. But do I know all the sides? At the moment I don't. So I've got this long side here, which is 8 centimeters. So this must be 8 centimeters, or this must be 8 centimeters. So this and this together would make 8. So that's 4, so this must be 4 as well. 4 centimeters, because 4 and 4 makes 8. Now I've got this length being 6, and this is 4, so this one, which fills the gap between, is 2 centimeters, because 2 and the 4, which is this one, make 6. So to work out the perimeter, I'll go 8, add 6, add 4, add 2, add 4, add 4, and I've come full circle, come back to where I started from. So I've got everything, and there are 1, 2, 3, 4, 5, 6 sides, so I've got 6 numbers in there. How can I add these easily? I've got 6 and 4 together, which makes 10, and I've got 8 and 2 together, which makes 10. So I've got 20 already, 24, 28. So 28 centimeters. And the last compound shape, we've got 9 kilometers. Obviously, this is scaled down because this is not really 9 kilometers, or this one is not 8 meters, or this one is not 4 meters. So it's like a plan, and we're using a scale to make these smaller. So we've got 9, so this and this together will make 9. That's 6, so this must be 3, which is this one as well. So 3 kilometers. And we don't know this, but we know this being 4, and this one here is 2, because it's the same as this one. So 4 and 2 makes 6 kilometers. How do I work out the perimeter now? So I'll go around 6 plus 3 plus 4 plus 6 plus 2 plus 9. So I've done everything, I crossed them out. So we'll try and match them together now. 4 and 6 makes 10. Now 6 and 3 makes 9, and I can borrow 1 from that to make 10. And then that leaves me with 1 there, and the 9 makes 10. So 10 and 10 and 10 makes 30. So 30 kilometers. Of course, you could have added as you wanted these without pairing them up. So you could go 6 and 3 makes 9, and then add 4, and then add 6, and add 2, and add 9. However you want to add them. But this is how you actually work out the perimeter of squares, rectangles, and compound shapes. We'll now look at the area. So area, different from the perimeter, it's about working out all of it inside, not outside. So area begins with A and means all of it inside. So examples when you need to work out the area is when you want to work out how much carpet you need to cover a room. So anything on the surface and it covers it all. Let's have a look at this square here, which has 4 meters, so it's a scaled down plan. So it is much smaller here in the drawing than it is in real life. And we'll see, so if you have little squares to cover this area, because carpet, for example, comes in squares, in square meters or square centimeters. So as you can see, I can fit 4 of these squares because 1 meter is represented by a centimeter. So I can fit 4 on this side and 4 on that side because it's a square. So if I try and fill all of this with little squares that are 1 centimeter both sides, we'll see that we can fit 16 of them, because 4 times 4 makes 16. So to work out the area, what we do is 4 times 4 equals 16 meters squared, because there are 16 squares. So that's how you work it out. And the same thing would happen here with this bigger square. So that is 7 centimeters the side, and of course the other side will be 7. So if I try and fit squares in there, how many can I fit? I would fit 7 along this side. So 1, 2, 3, 4, 5, 6, 7. Try and draw them rather than put the squares in. So there's 1, 2, 3, 4, 5, 6, 7, and 7 on that side as well, and 7 here as well. So 1, 2, 3, 4, 5, 6, 7. So if I filled it in completely with squares, centimeter squares, it looked like this. So pretty similar to what we have here, it's just bigger. So 7 on this side and 7 on this side. So altogether it will be 49, because 7 times 7 equals 49. And what's the unit? Is it centimeters? No, it's centimeters squared, because we actually multiplying 2 dimensions here, aren't we? 7 times 7, so the length times the width, and that's we have a 2 there, and that 2 represents squares as well. Now looking at rectangles is the same thing. So that's 8 meters and 3 there, so that would be 3, and that would be 8 along the length. So 3 times 8 equals 24, and that's meters squared. And I won't go through the squares here because now we get the idea. So the width is 4, the length is 6, so we go 4 times 6 equals 24 meters squared. Notice how they have the same area, although they're different rectangles, they have the same area, because both 8 times 3 equals 24 and 6 times 4 equals 24. Now compound shapes, so to work out the area we needed the length and the width. So we'll need now to break these down, to cut them into 2 shapes. So I'll make 2 rectangles, so I could do it here, I'll cut these here or there. It's perfectly fine either way. I'll just pick the one that is easier for me. So if I want to cut it here, let's see, so this area would be worked out by the length times the width. So the length is 8 and the width is 4. It's not 6 because 6 includes this bit as well, so that tells me that this must be 2. This bit here must be 2 centimeters. So 8 times 4, I'll work it out here, 8 times 4 equals 32, and this that remains now, the width is 2, but what is the length? The length, we'll try and work it out. So this and this will make 8, so 4 and 4 makes 8. So that this one here, this area here, is equal to 4 times 2, which gives 8. So 8 centimeters squared plus the 32 equals 40 centimeters squared. The next one, let's cut it at this point. So we've got one rectangle here and another one there, so let's have a look. This one, can we work it out? We've got a 6, so length is the 6, width is 2, so 6 times 2 equals 12. How about this one? Do I know that width? No. And so I will need to work it out. So this whole length is 9 kilometers. This one is 6, so this one either here or there must be 3, because 3 and 6 gives us 9. So 3 kilometers. So I've worked out one. The next dimension we've got, right, this whole thing we don't know, but we know this is 4 and this one 2, because it's the same as this one. So 2 and 4 make 6, so 6 kilometers there. Now I've got the width and the length. 6 times 3 equals 18. So altogether the whole shape is equal to 12 plus 18 gives us 30 kilometers squared. So again, to recap, we said area covers it all, so we must make sure we cover the whole of the shape. So we are actually multiplying when it comes to area, because it's about how many squares would fit in, just like in the examples we've looked at. Compound shapes, then it was a case of splitting them into 2 shapes. If you've noticed, the answer there was a square number, because this shape was a square. So 7 times 7 gives us 49, 4 times 4 gives 16, 6 times 6 gives us 36. So all the answers of the areas for the squares will be square numbers. In this video we're going to calculate the volume of cubes and cuboids. So I have a cube and a cuboid, but I want to link this to the previous lessons on perimeter and area. When we looked at perimeter, it was about going around a 2D shape like that. So if that was the plan of the room, we'd be talking about things like skirting boards that we need to put just around on the rim. So if I take a measuring tape or a piece of string and go around, it's going to look like this in the end. So we measure it in centimeters or meters, because it's just the length. Whereas if I want to cover this, maybe with wrapping paper, or when it comes to a room I want to put carpet in, then actually looking at the whole surface area. So that's counted or worked out in squares. So this would be centimeter squares or meter squared. And you see it too at the top, which suggests that we're looking at 2 dimensions. We're looking at the length and the width. We're multiplying them, and that gives us the 2. When it comes to volume, we're not looking at the flat 2D shape any longer. We're looking at the 3D shape, 3 dimensions. So that's the length and the width, but we're considering the depth as well, how deep or how high it is. So I worked this out, and it was 9 on the surface area, but there are 3 layers of it, so that's just 1 layer, 9, but I've got another layer here to make another 9, and another layer at the top to make another 9. So that's 9 and 9 and 9 all together, so that is 27. And how do I write that? What unit do I use? That's centimeter cubed, because we are looking at 3 dimensions. So we've got the length and the width that we already used when we work out the surface area, that gave us 9, and we looked at the depth as well, how many layers are on top of each other. So that's 3, 1, 2, 3 of them, and it can be expressed in meter cubed, kilometer cubed, and so on. So when it came to volume, we're looking at 3 dimensions. So it looks something like this. So I already said this was 27 centimeters cubed, because I'd already worked out the area before, the surface area of the square, any of them, because it's a cube and it doesn't matter. So I'd worked it out before, and that gave me 9. And then I said, oh, okay, there is one layer, there's 2 and 3, so 9 lots of 3 or 3 lots of 9, and that gave me 27. But I could also say, okay, when you work out the surface area, what I do is 3 times 3. That's how I worked it out. That's what I did here as well. So 3 times 3 times 3 as well. So I could say 3 times 3 times 3. So I am taking account of all 3 of the dimensions. I'm taking account of the length, the width, and the height. So 3 times 3 times 3 equals 27 centimeters cubed. Or the other way was to have the surface area, which was 9 times 3, and that's again 27 centimeters cubed. We'll now look at the cuboid. So let's use both of the methods. Let's work out a surface area first, either this one or this, it doesn't really matter. Okay, so I've got 1, 2, 3, 4 at the bottom, which is 2 times 2, so that's the surface area of one of the faces. So that's 4. Now that's the layer at the bottom, but I've got 1, 2, 3, 4 more, so it's 5 in total. So 4 times 5, or 5 times 4, gives me 20 centimeters cubed, because these are centimeter long. And the other way would be, okay, so the 3 dimensions, length, width, and height. So length is 2, width is 2, height is 5. So 2 times 2 times 5, that makes 20 again. 20 centimeters cubed. Because we're looking at the 3 dimensions, as I said, and we're looking at how many cubes fit in there. So what a volume gives us is how much space an object takes, or how many smaller items you can fit, and those smaller items are cubic centimeters or cubic meters, depending on how big the object is. So if I'm given a cube like this, and I've got information that this is 4 meters, this is 5 meters, and this is 3 meters. So the length 4, the width 5, and the height or the depth 3 meters. So to work out the volume, this is what I'm going to be doing. I'm going to be working out this 4 times 5 times 3. So 4 times 5 is 20, times 3 is 60. 60 meters cubed. Don't forget, it's 3 of them, the 3 dimensions. And we're fitting in cubes inside. We're imagining cubes to be fitted in. Now, one more, if we have a cuboid again, and let's say this is 2 kilometers, this is 8 kilometers, and this is 3 kilometers. So we're going to go 2 times 3 times 8. So order does not matter as long as we take into account all 3 of them. So 2 times 3 is 6, times 8, 48. 48 kilometers cubed. So we've just looked at how to calculate the volume of cubes and cuboids. And again, when it's clear how many cubes go into the shape, you just multiply or count them, and it was length times width times height. However, in some other questions, you might be asked how many of these smaller items fit in a bigger item. And to illustrate, I've got some boxes in here. So real life, a box of dominoes, how many dominoes would fit in there? Or this other plastic box, and I've got some centimeter cubes that I'll try and fit in there. Now, in this case, I would not encourage you to go and measure the length, width and height and multiply them together and try and fit in as many centimeter cubes. So that might work, but might not work as well, and I'll explain why. I would rather try and fit in as many as I can of these along the length, the width and the height, because there could be some space left but not enough to fit in extra cubes. So we'll look at what that means. So if you look closely, there is some space left there, but I can't fit a cube. So if I calculated that in, or took it into account when working out volume, it could give me a bigger answer, but it doesn't mean I can fit more cubes in. So again, same thing with the width. There is more space there left, but I can't fit another one. So we'll try and see how many it fit along the height. So if I close the box, yes, I can close it, and I can't fit any more of them at the top. So what do I do at this point? So I've laid them out, and if I haven't got a real box, it'd be a case of marking the picture, the drawing that you have in the question. So there we go. We've got 1, 2, 3, 4, 5, 6 along the length. We've got 1, 2, 3, 4 along the width and 2 along the height. So now what I can do is I can multiply that 6 by 4 by 2. So that means I've got 6 along the length and then 4. So if I try to fill this in at the bottom layer, there would be 24 cubes, because 6 times 4 or 4 times 6 gives me 24. But I can fit, as we said, another layer on top. So 24 and the 24 makes 48. So the number of cubes that we can fit in is 48. And this would answer your question correctly, rather than if you worked out the volume of the box and the volume of the cube and divided the volume of the box by the volume of the cube, because of the spaces that could be left and which can not be enough to fit in extra boxes. So if I'm given a question like this on paper, I would supposedly have a drawing, or if there isn't a drawing, then I would try and draw the box myself. So a cuboid or a cube, depending on the question. So if it's exactly like this, then I would say try and measure it, or if it's given the measurement to me, then I'm going to try and fit as many as I can. So if this is 6.3 centimeters and I'm told that the cubes are centimeter cubes, I'll go and try and fit them in. 1, 2, 3, 4, 5, 6. So there is some space left. So that's the only thing that I need to consider. How many of them would fit exactly if we asked to fit in boxes in there, and not the volume. So that's the one. And then if this is, let's say 2.4, I can only fit 2 of them, so there would be some extra space in there. but I don't need to consider that when it comes to number of boxes that can be fitted. And if this is 2.5, I've got only 2 in there. So I've got how many boxes can I fit along the length? That's 6. How many can I fit along the width? That's 2. How many, in actual fact, we had 4 along the width, so we'll use the example we had, so that's 4. And how many can you use along the height? That was 2. So then you go 6 times 4 is 24, times 2 is 48. 48 cubes. So notice the difference between working out the volume, because if I'm just given a box and I'm asked work out the volume of this cuboid, then I would multiply the dimensions. I'd go 6.3 times 4.3 times 2.4, and I'd write my answer in centimeter cubes. Actually, we can try and do that now. So 6.3 times 2.4 times 4.3, that is 65.016 centimeter cubes, or cubic centimeters, or centimeters cubed. So I did 6.3 times 4.3 times 2.4, and that gave me this answer. So that's the volume. And let's show now what that means if I divided this by the volume of the small cubes. So the volume of the small cubes is actually 1, because they're 1 centimeter cube. So 1 times 1 times 1 gives me 1. So if I divided this volume of the big box by the volume of each cube, which is just 1, I'd have 65 cubes presumably fitting in. But was that the case when we looked at them, when we tried to fit them? Was that the case? Because here we're taking into account the gaps as well, the small gaps along the length, along the width. If you remember, these small gaps, now they're adding up and creating this extra volume, which when it comes to fitting in boxes doesn't really work. So it's really paying attention to the question. If you're asked to work out the volume, by all means just multiply length times width times height, or area times the height. But if you are to work out how many of the smaller items into the bigger ones, take it in steps and find how many fit along the length, how many along the width, and how many along the height. In this video, we'll learn to draw 2D shapes and demonstrate an understanding of line symmetry and knowledge of the relative size of angles. I'll start with the relative size of angles, because that's going to help us with the line of symmetry and drawing 2D shapes. So I've got a few angles here. I've got a 90-degree angle, which is the ones that we find in the corners of the papers, or corners of the rulers, corners of the room as well, and we can measure them with a protractor as well, so it go up to 90 degrees. This line we call perpendicular line, so it creates 90 degrees if you're interested to know. Now we've got angles which are smaller than 90 degrees, like this one, that's 49. So any number of degrees that is lower than 90, maybe 80, 65, 73, 2, 5, any number of degrees, we call this acute. So that's what we call acute angle. a way to remember is, like, since it's a small thing, it's like the small things in life, we call them cute. Little babies are cute, or tiny things that we say, oh, this is cute. So acute angle. When it's an angle is larger than 90 degrees, so it looks like this. So this is 100, it could be 110, 105, 106. Anything that is bigger than 90 but it's smaller than 180, which would be a straight line. Okay, what we call this? Obtuse. What we call it is obtuse angle. And one way to remember is, since it's larger than 90 degrees, is obese. So that's a way to remember it. And we have other angles like these ones, which are larger than 180, and they are reflected on the other side as well. So reflex, we call them reflex angles. So reflected, reflex. So we've looked at these angles and how they compare to the 90 degrees or the right angle as well. Now we'll actually try and draw 2D shapes. So we'll start with a square, and we know that a square has equal sides, so we'll make this a square of 3 centimeters. So 3. Now we'll do the next side, but we shouldn't forget that this got to be a right angle here, because otherwise it won't work. We'd end up having a different shape completely. So I will make a right angle here and then measure it to be 3 centimeters. And I can check whether I've got this as 90 degrees, and that is spot on 90 degrees. And I need to do the same with this one as well. So aligning it, 90 degrees is there, so this must be up to that point if we connect the two. So I will go up to 3 centimeters, and then of course these two, we don't need to measure the angles because we just can connect the dots. But if we want to make sure, just check it, and it is 90 degrees. So the sides were the same, 3 centimeters, all of them, and the angles 90 degrees. So all of these 90 degrees, because what can happen if we don't measure these correctly is that we'll have, so let's say I'm trying to do 3 centimeters again, and I'll do 3 centimeters again, and connecting these two together. Do I have a square now? No, I don't. That has a different name, which is called a parallelogram. So that is a square. Angles and the sides are really important. Now we'll try and draw a rectangle. So a rectangle, we know it has some longer sides, 2 longer sides, so we go, let's say 5. Well, I extended it a bit, so I'm going to make it 6 now. 6. And let's make this 3. But have I actually measured the angle? Have I done it correctly? That is right. And I'll measure this as well. So that is 90 degrees. And 6 centimeters. Now again, I want this to be 90 degrees as well, and it is if I just connect these two ends of the lines. So again, 90 degrees, 90 degrees, 90 degrees, and this was 6 centimeters, this was 3 centimeters, different lengths. So we've done a rectangle as well, the square and rectangle, and we'll have a look now at drawing a triangle. So there are different types of triangles. I could do one where I don't care about the angles at all and different sizes of sides. So if I extend it a bit more, so that's a triangle. We have another type of triangle, which is the right angle triangle. So a right angle suggests that we need to have a right angle, so I will measure 90 degrees, connect the points, and that is so 90 degrees. So that is the right angle triangle. This is scalene 1, and there are another two types. The one where you have two of the same angles, two angles which are the same, in other words. So if I make one 50 degrees, so will be the other one on the other side at the base. So 50, that is 50 as well. So if I just connect the dots, there we have the triangle. So these two are the same. This is what we call an isosceles triangle. And finally, there is this special type of triangle which has all the sides the same and all the angles the same, and it's called equilateral. So equal, all sides are equal, and in order for them to be equal there must be 60 degrees, 60 and 60 and 60, because all together all the angles in a triangle make 180. So I'll go, there we have 60, and I'll measure 60 on the other side as well. So if I connect these together, I've got a triangle which has all of the angles and the sides the same. So this side is the same as that and the same as that as well. So there are three types of triangles. We looked at a square and a rectangle. A circle is really important as well, so we'll draw a circle as well. With a circle you don't need a ruler, but you need a compass. So the way you start it is through a point, the dot, and put the pointy part of the compass on it, and then just draw the circle like this. So that's the center of the circle. Make sure you don't move this around so the center doesn't change, because otherwise you'd have a different shape, not a circle. So the other two shapes that you need to know are the pentagon and hexagon. In order to know how to draw them, it's important that you know how many degrees in each angle. So I'll link it to what we've already done. So with a square, we said each and every corner would be 90 degrees. So 90, 90, 90, 90 makes 360. So all together 360 degrees. And the same thing with a rectangle, 360. So what we know is that when it comes to these shapes with four sides, which we also call quadrilaterals, their angles add up to 360. When it comes to triangles, it only takes up half of it, because a triangle is like a square or rectangle being cut in half. So all of these add up to 180, 180, 180, 180, 180, no matter what type. So these add up to 180. Obviously a circle doesn't have any corners, but this will link to what we're going to be doing next, because if you recall, a pentagon, a regular pentagon, and that's what we're interested in, looks like this, and it has equal sides and equal angles. So what this is going to mean is that we need to know exactly how many degrees there will be all together. And the easy way to work out or to find out is to split this into triangles. So start from a point and split this into triangles. How many triangles have I created? There are 3 of them. So 108 in here, 108 in there, and 108 in there. So each triangle, as we said, has 180 degrees. So 180 plus 180 plus 180. So that's 24. So 4 down and 2. 2, 3, 4, 5. So 540 degrees, all of these together. But we're going to have to split them into 5 because they're 5 angles. So 540 divided by 5. How many 5s would fit into 5? That's 1. How many 5s would fit into 4? That's none. So I put 0. Now into 40, how many 5s? That would be 8. So each angle must be 180 degrees. So let's actually draw it. So I'll start off with a line. Easy to do it at the bottom. So let's make this 3 centimeters, because there will be equal sides as well. So I need to make now this angle 108 and this 108. So I'll go starting from 0 and measuring 108. So we'll go to 108. That's this point here, and on the other side as well for the other angle. That's going to be starting from here, 108. So I've got that already. Now I'll need to measure the sides, 3 centimeters as well. So now I need to measure the next angle here, which needs to be 108 again. So we start from 0, 108. So connect these two, and there we have them. And there we go. We do the same over here, 108. So we go to 108 there. Now this must be 108 as well, so I'll double check. And and that is 108 as well. So I've got a pentagon, a regular pentagon that I've drawn. I will shorten these lines. So I've got a pentagon. This is 108, this is 108, this is 108, 108, 108. So there is my pentagon. And the final one we need to draw is a hexagon. So again, the idea of it is exactly the same as for the pentagon. So a pentagon will have 6 sides, equal angles, equal sides. So again, to find out how many degrees altogether, we're going to split this into triangles. So I'll go, there is 1, 2, 3, 4. So 1, 2, 3, 4. Each of them is 180 degrees because we said in a triangle that's how many degrees there are. So we'll add one more because there were 3 in a pentagon, there are 4 in a hexagon. So 540 add 180, so that's 0, that's 2, that's 7, so 720 degrees all together. Now 720 degrees, that is for all of it. So in each of the angles, how many degrees will there be? So 720 divided by 6. So how many 6s fit into 7? That's 1 remaining. 6 into 12 is 2, and into 0, that's 0. So 120 degrees each. So again, we'll start with a line. We'll make it 3 centimeters long, and we'll measure now 120 degrees. So we'll go 0 up to 120, and that's there, connecting. And then on the other side we've got 120 we need, so we go to 120 because we're starting from 0 here. 120, connecting the dots, and again it's going to be 3 centimeters long, so 3 there and 3 here. There we go. And 120, so from 0 to 120, which is there. So connecting these two as well. So again, 3 centimeters, that's got to stop there. 120 again, so that's this point here. Connecting, joining 3 centimeters, so it's got to stop here. Now if we just join these 2 dots together, it should be 120 as well. Yeah, so it is 120, and that's 120. So all of these angles measure 120, 120, 120 degrees. So I've just drawn a regular hexagon. So to summarize, we had the square and rectangle with 360 degrees in total. We had the triangles with 180, a circle which doesn't have any angles at all, and we looked at a pentagon. We split it into triangles and it added up to 540 degrees, so we split that into 5 equal parts and that suggested that it was 108 degrees each corner. And with a hexagon we added them up and it was 720, so we divided that by 6 to give 120 degrees in each of them, and that's how we constructed a pentagon and a hexagon as well. Now we'll look at the lines of symmetry. So the lines of symmetry are based on the angles and the sides as well. So what we've just done should help us with constructing lines of symmetry, accurate lines of symmetry. So if you look at the square, if I cut this halfway through like this, so that is, it was 3, I'm going to cut it in half to 1.5, so 1.5 again, connect these together, and that's a line symmetry because both sides reflect each other. And I could do the same thing on the other side, so that's a 3, so there's going to be 1.5, 1.5, so this is another line of symmetry. With a square, however, you can have these lines of symmetry as well, because this side is reflected on the other side as well, and you can have another one like this. So it has 4 lines of symmetry. What about the rectangle? Does it have 4, less or more? Now again, cutting this in half by measuring accurately, we can do this, and also on the other side I can do this and it would reflect. Can I do this one, this line of symmetry? No, I can't, because then this corner would come over here and this corner would come over there. So it has, a rectangle has only 2 lines of symmetry. What about this triangle, the scalene triangle, which we said had no equal sides or angles? So this has no lines of symmetry at all because none of the sides reflect the other. What about this one? Now if this angle is not the same as that angle, then this has no line of symmetry. Whereas this one here, this one has 2 equal angles, which means these 2 sides are the same. So finding the midpoint here, that's 6, so it's going to be a 3, connecting it with the other corner, and that's 1 line of symmetry. What about the equilateral one? So if we look at equilateral, we said all sides are the same and all angles are the same. So if I cut this in half to 2 and connect it with this corner, that's 1 line of symmetry, it's reflected. But the same thing would happen over here if I cut this in half and connect it with this, so that is reflected as well. And the same thing would happen on the other side, so we'd have cut this in half, connect, and so that equilateral triangle has 3 lines of symmetry. And if we look at the pentagon, again equal sides and angles, so halfway through, that's 1.5, connected with the angle on the opposite, and that is what you get, a line of symmetry, another line of symmetry here, another line of symmetry, and we can have one more here and one here. So how many lines of symmetry do I have? It's 5. 5 sides, 5 equal sides, 5 equal angles, 5 lines of symmetry. And as you would expect, we'd have many lines of symmetry here. So first of all, if you cut this at this point, we'd have a line of symmetry because it's reflected both sides. And if I do it here as well, that would be 2, that would be 3. Now I can cut this in half by measuring both sides to be precise. So there we have another one, and I can do that here and there. So there we go. So we have 6 lines of symmetry in a hexagon. So this should show you how many lines of symmetry. What about a circle? How many lines of symmetry does a circle have? If I cut this through this point, I'd cut the circle in half. If I did it here, I'd cut the circle in half again. If I did it here, I'd cut the circle in half. If I did it here, I'd still cut the circle in half. Still, so this means that a circle has many lines of symmetry. It has many lines of symmetry. So a circle has an infinite number of lines of symmetry. In this video we'll learn to interpret nets of simple 3D shapes. So I've got 6 simple 3D shapes, and actually they're nets on this whiteboard, and I'd like you to just think which of these shapes they would make. Is it a cube, cuboid, pyramid, square-based pyramid, or triangular-based pyramid? We've got prism and cylinder. So try and match these names with the actual nets of the shapes. I've added the names of the shapes now as well. So let's start with the first one. So this is the net of a cube, and we can see it has square faces. There are 6 of them, and we know that a cube has 6 square faces. So if I put these faces together, I would be able to make a cube. As you can see, so going back to the net, we had 4 faces next to each other at the center. There's 2 faces on the side. So what would happen if I moved this over here, or there, or here? It'd be the same thing. As you can see, you'd become part of the cube. So it would not matter whether it was connected here or here or any of the 4 sides really. And if you want, I can show you what that means as well. So I'm gonna cut it off and then stick it to another side. And again, if I try and bring these all together, it still makes a cube. As you can see. So it does not matter whether this face on the side is stuck here, 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 or here. So it can be any of these sides. The same thing happens on the other side. So if I remove this face and I maybe place it here, it would still make a cube. I'll show you that. so it could be anywhere. Putting it together now. And we've made a cube. It's not a perfect cube, but it still is a cube. Now we're looking at the cuboid. What is different? Now we've got 6 faces, but they are of different sizes. So we have these 2 being the same and these 4 being the same. And that's the cuboid, because the cuboid has 4 rectangles and it has 2 squares in this case, but it could have all 6 rectangles as well. So as you can see, we've made a cuboid. Same as with a cube. If I unfold this again, and if I try to place this face here, of course I can't place it here because this is longer than this and then this. So if I remove this and place it here, it'd be the same thing, and I could do the same with this face. Rather than have it here, I could have it over here. Can I cut this off and turn it around so that this would fit in there? I could do that as well, and we'll see that now. So you can see that this falls into this and falls into place, but I could cut it off as well, and that could be stuck here or here. So that's changing the shape of the net slightly, and this is a good thing because then we've prepared for all sorts of nets, so we can interpret them, we can identify them. So I'll cut off this other one as well. And rather than placing it here, I'll place it over here. And you see how the net has changed. Let's see, can we still make a cuboid? Yes, we can. There is our cuboid. So we'll place it next to the cube, and we'll now look at the square-based pyramid. So the center is a square, as the name suggests, square-based pyramid, and then we have the triangular sides as well, which will form the pointy pyramid at the top. So all these 4 triangles are the same size, and we have a square at the bottom. So what else could we see? How else could this net be constructed? This is the typical shape of a square-based pyramid. So this is how you'd normally see it and identify it. But of course, these triangular faces could be joined together rather than to the square base, and that would still make a square-based pyramid. So we'll show you now. If I cut it off the base, and if I stick this triangle next to the other triangle, we've got the same length, these two sides, and sticking them together, I could then still make a pyramid. However, as I said, the typical shape of a net for the square base pyramid is this, and I'll put it together to make the pyramid. We'll now look at the triangular base pyramid. As you can see, there are 4 triangles. There is a triangle at the base, and we have these 3 other triangles of the same size attached to the base. So putting these together, very similar to the square-based pyramid. The only difference is that we have a triangle at the base. So putting these all together will give us the pyramid. And looking at the prism, as you can see, there is a square or a rectangle at the base. We have another 2 rectangles and 2 triangles on the side. So putting these together gives us the prism. We could have this triangle over here as well, or on this side, and the same thing with the other triangle, just like the cube and the cuboid. Finally, we'll look at the cylinder. So as you can see, there is a rectangle which is put together to make the cylinder, and on the sides we have these 2 circles. So that makes the circular faces of the cylinder. Now, in terms of the position of these circles, they could be anywhere, either here in the middle, or they could be right at the edges, and it does not matter because they will all come together to form this cylinder. So sticking the faces together will not give us a perfect cylinder, but I think we get the idea through this. Sticking the other circular face, and we have a cylinder. You can practice this yourself by printing out some nets of these shapes, cutting them out and then sticking them together, or maybe unfolding boxes or packaging of different items that you might have bought, like cereal boxes, for example. In this video, we'll learn to interpret plans and elevations of simple 3D shapes. So we'll start with a cube, then we'll look at a cuboid, a prism, square base pyramid, triangular base pyramid, and a cylinder. So starting with a cube, what does plan mean and what does elevation mean? So plan is whatever you see from the top of the shape. So this is the plan view of a cube, and what you can see at the top is just a square, and that's what we're going to draw here as the plan. The elevations, we have the front elevations, so whatever you can see at the front, and the side elevations as well, so whatever you can see on the side. So let's start with the plan. So I'm going to draw a square, but I need to measure the dimensions of the cube. So we've got 5 centimeters by 5 centimeters. So we'll start right here. So we've got the plan, and looking at the front, this is identical and it's the same measurements, because as we know, a cube has 6 faces of the same size. So we'll do the same here for the front elevation and for the side elevation as well. So as you can see, these look identical. We'll now move to the cuboid. So doing the plan first, what we can see from the top is a rectangle. I've measured the dimensions and it's 7 by 4 centimeters. These are all right angles, 90-degree angles. So I've got the plan here. In terms of the front elevation, it's going to be identical because this face is identical to this one for this cuboid. So I'll do the same thing over here. The side elevation, however, is not identical. We've got 4 centimeters by 4 centimeters, so a square that is 4 centimeters wide and 4 centimeters long. Then we have the side elevation of the cuboid. So we'll now look at the prism. From the top, what we can see is a rectangle which has a line through in the middle. So we'll measure the dimensions. I've checked this out and it's 7 centimeters by 6.4. So we'll draw the rectangle first. Now the line goes in the middle. So this was 6.4, so 3.2 is halfway through. 3.2 on the other side as well. Join these 2 dots. And then we have the line in the middle as well. So this is the plan. Now we'll look at the front elevation. So at the front we just see a rectangle. However, we need to be careful to not just measure these dimensions because this is not the real height of the prism. The height of the prism could be measured here. So that's what we're gonna use. This is the length, so we can use that, and it was 7 centimeters as we said earlier. Now this is going to be, this is 5.5, so we'll leave a gap and this is done, so we can call this the front elevation. And we'll now look at the side elevation as well. As you can see, it's a triangle, so we'll get the base, we'll measure the base, which is 6.4, and we know that this is 5.5, so we'll start with the base. And we'll halfway through this, so this is 6.4, 3.2, we'll draw a perpendicular line, which you can use a ruler to help you with, but also the graph paper helps. So this line needs to be 5.5 centimeters long. So 5.5 is right here, so this is where we're going to need to stop, and we'll use these points to make the triangle. So I need to get rid of this line in the middle now, and we've got the side elevation as well for the prism. Now we'll draw the plan and elevations of a square-based pyramid. So starting with the plan, what we can see is a square and we have these diagonal lines going across. So we'll measure the dimensions of the base. So we're talking about 6.6 centimeters. And it's a square, so the other side will be 6.6. We need to draw the lines on the top, so this is what I'm going to do. And there we have the plan. Now we'll look at the front elevation. So we've got a triangle that we need to draw, so I can measure the base, which was 6.6 anyway, and we need to make sure to not measure this because this is slanted height. We've got to measure the real height of the pyramid. At this level, you're not required to know how to work this out. I'll give the measurement to you, and it's about 8 centimeters. So this is the front elevation, and the side elevation in fact will be identical. This is the case with the square-based pyramid. So we'll draw another one that is identical to this, another triangle. So here we have the side elevation as well. Now we'll look at the triangular based pyramid. The process for the triangular based pyramid is very similar to the square based one. So the only difference is that we've got a triangle as the base as well. So we're going to have to draw a triangle which is going to look like this. So we'll take the measurements of the base, and it is 9.6, and the height, so somewhere in the middle, 9.6, halfway through is 4.8, so about here is the point where we're gonna measure the height, which is 8.5. Getting rid of this line in the middle. Now, so this is the base, and it does match the shape. Now we'll look at the front elevation and the side elevation, which will be identical. For the front elevation, again, we've got the base, the length of the base, and we put the height. So the height, in fact, we cannot measure the height of the pyramid, we cannot measure over here. It's got to be inside. So you wouldn't be able to do this at this level, so I'll give it to you. It's about 8 centimeters. So we'll make this about 8 centimeters high. So I've put these together. The front and the side ones look identical because the height is the same, whereas the plan, the triangle for the plan, is not of the same height, as you can see, and that is perfectly fine. So looking at the cylinder, all we can see from the top is a rectangle. So I've measured the dimensions of this beforehand, and it's about 10.5 centimeters long and about 5 centimeters wide. So I'll draw that. So we've got the plan. In terms of the front elevation, it is identical to the plan, as you can see. So we'll draw an identical rectangle over here. In terms of the side elevation, as you can see, there is a circle here. So we're going to have to draw a circle. And I've given you the dimensions, which was 5 centimeters from this point to this point. We call this the diameter. So the radius must be 2.5 centimeters. Now, you're not required to do this at this level. However, it's good to know. So 2.5, and I'll put a dot for the center. So this has to stay still. So there we have the side elevation. At level 1, you're not likely to be asked to draw plans and elevations, but I drew them for you so that you can see what they are. So hopefully this is going to help us interpret them now. So if I show you this, what kind of shape would you think this is? So thinking of the 3D shapes, and we've got a plan which is a rectangle, we've got a front elevation which is also identical, and rectangles we've said we've got in cuboids, and the side is a square as well. So this is a cuboid. Looking at the next one, we've got square, square, square. Plan, the front and the sides are squares. So this is a cube. And looking at this, it looks like a rectangle at the top, but it has a line across. So that was the shape that we looked at earlier, and it's the prism. And the side is a rectangle, so that confirms it's a prism. And triangles all the way, triangles at the base, triangle on the side, triangle on the front. This shows that this is a triangular base pyramid. And looking at this one, it's a square at the base. We can see diagonal lines at the top, and at the front we can see triangles, on the side we can see triangles. So this must be a square based pyramid. And we've got a rectangle from the top, we've got a rectangle at the front, but there is a circle on the side. So the only one with a circle that we looked at was a cylinder. In this video we'll learn to use angles when describing position and direction, and measure angles in degrees. We'll start by measuring angles in degrees first, because you're going to need that when describing position and direction using maps, for example. So what you'll need is a ruler and a protractor. I always encourage learners to use pencils rather than pens when drawing, because they might get it wrong, so then you could easily rub out whatever answer you think is wrong. So we'll start by drawing a line first. So what I'm doing is I'm constructing an angle, drawing an angle, in other words. So I'll start by drawing a line, and then we'll use a protractor to draw an angle of 100 degrees. So you will see that 100 is there, but it's also there as well. And why is that? Because a protractor, you know, can be used or works in similar ways to a calculator. So it starts from 0. So if your angle starts here, or you start measuring your angle here, then you go 0, 10, 20, 30, 40 and so on this way. But if your angle is on this other side, then you'd start from this 0 here, so 0, 10, 20, 30, 40, 50, 60 and so on. So it depends on where your angle is, and we'll do both of the sides as well. So if you look at this, I want to draw a 100-degree angle on this side. So what I'm going to do, I'm going to take the protractor and put the end of this line right in line with this cross here. So I'll place it right on top, and the line of the protractor is aligned with the line underneath, so it's right on top of it. Now I want to draw my angle here, so I'll go from the line, so 0, 10, 20, 90, and we're going to 100, so that point is right here. So I connect these two points together, so this angle now is 100 degrees. And the way to check it also, this is bigger than 90 degrees, because a 90-degree angle would come to this point, so this is larger than 90 degrees, and 100 degrees is larger than 90 degrees. Now we'll draw another one over here. So there is a straight line, and I'll draw it on the other side this time around. So that means I'm going to have to align it with a protractor, so right on top. This means the end of the line, and this line on the protractor is on top of the line I drew. So now I've got to start drawing, it's got to start counting from 0. So 0, 10, 20, 30, 40, 50 and 60, 70, so I'll go to 100 because that's the angle that I want. So now it is this angle, this side, 100 degrees as well. So both of them are 100 degrees. This is on this side and that is on the other side. Now we'll measure one angle. So I'm gonna randomly draw an angle. It's this one that I'm after, so it's marked there. So what do? I can start in any direction, it doesn't matter. So I'll suppose this is my straight line, and there we go, aligned carefully on top of that corner, and we're starting from 0, so 10, 20, 30, 40, so it's over 40, not 50 yet, so it is about 49 degrees. So it's about 49 degrees. Now we'll try and do it on the other side, the same angle. So I will align it carefully, start from 0, so 0, 10, 20, 30, 40, again not 50 yet, so about 49. So that is 49 degrees. Now we'll try and measure another angle. So I want to measure 210 degrees. So I will try and do it this way. So 210. As you can see, you start from 0, this goes up to 180, but 210 is bigger. So I'll put a mark there and I'll turn this around. So 210 I said I want, and I've got 180 already. It's a straight line. So how many more degrees do I need to make 210? So that is 30 degrees. So I'll turn this around, so that means I've got this already and I need more. So I need to continue with the rotation. So if you go there, align it again, so that matches with the 0 there. So now we're starting again from 0 and going to 30. So 10, 20, 30. So that's the point. that we need to connect with the center, and we continue this angle. So now this angle is 210 degrees. So this is 210 degrees. What I'm going to do now is I'm going to try and describe position and direction using a map. At entry 3, we looked at a map and we identified 8 compass points, which were north, south, east, west, northeast, southeast, southwest and northwest. Now that is a useful way to describe position and direction, but we'll try and be a bit more precise this time, because what if a place is right here? So it is within maybe northeast, but is it more like north? So we'll try and measure the degrees, measure the angle to be precise, and we'll use the map to do that. So we'll pick 2 different places, Glasgow and Edinburgh, and we'll try and find what we call the bearing of Edinburgh from Glasgow. So the wording suggests from Glasgow, that suggests that we start with Glasgow, and we always start from the north. So I'm gonna use this ruler to draw the north of from Glasgow. So there is a straight angle there. So we've got Glasgow. Now we're moving from Glasgow to Edinburgh. So what is that bearing? In other words, we're looking for this angle. So always we start from the north and we go clockwise when we measure the angle when it comes to bearings. So maps should remind you of that. So I'll start from the north, so that's 0 there. I'll bring it closer to the camera. So we'll start from 0. As you can see, so that is, you see where this center is just on top of the city where we're measuring from, so Glasgow, and the line that I drew, the north, due north, is in line with this line of the protractor. So there we go, 0, 10, 20, 30, 40, 50, 60, 70. Now, as you can see, this is a short line. So in order to be accurate and measure exactly how many degrees this is, I need to extend the line. So I'll put this down and extend the line between Glasgow and Edinburgh, so I can be more precise when measuring. I need to keep this down when measuring, but I need to bring it up so that we can read this close to the camera closely and accurately. So again, a line, start from 0, so now it's easier to read it. So we get, as you can see, we have 0, 10, 20, 30, 40, 50, 60, 70, not 80 yet, but 75, 76, 77. I'd say this is closer to 77, so this is about 77 degrees. So 77 degrees. But bearings, we write them with 3 digits. So if there isn't 100, 200 in there, or 300, we'll put 0. So that's how we write the bearing. It's still 77 degrees, we just put a 0 in front. So the bearing of Edinburgh from Glasgow is 077, which is 77 degrees. So that's how you'd read it. The bearing of Edinburgh from Glasgow is 077 or 77 degrees. Now we'll have a look at another bearing. So we'll have a look at Dublin. So the bearing of Dublin from Cork. So there is Cork, so it says from Cork. So that's my starting point, from Cork. And we look at drawing north first, a line towards north, and that's the top of the paper. So trying to get a 90-degree angle there, so it goes north, right? And we set from Cork, so the bearing of Dublin from Cork. So we're going to Dublin. So from Cork, that means we measuring this angle. So again, I'll take my protractor and align it. There is the angle that I need to measure, aligned, starting from 0. So I'll go again. I need to make this line a bit longer so that I can work out precisely the number of degrees or read the measurement. So there we are. Aligning the protractor, starting from 0. So we go to 0, 10, 20, 30, 40, 42 degrees. This is 42 degrees. As you can see, that is 42. So I'll write the full sentence. So we're saying the bearing of Dublin from Cork is 042 degrees, which is 42 degrees. What would be the bearing of Inverness from Aberdeen? So Inverness is there from Aberdeen, so we're starting with Aberdeen, drawing north. So that's the line that represents north, and we're going to Inverness. So that means we're going this way because it's always clockwise. We're starting from north, always we're starting from north, and we're going clockwise. So that means I'll go through this, and what this suggests to me is that it will be more than 180 degrees, and I can easily just continue this line. So that's the point where Aberdeen is. I'll continue this line. So this is going to be 180 degrees already, and I need to add up this angle. So I need to add those degrees on top. So there we have the 180 degrees already. We need to add this as well. So I'm not going to measure this. this part because I know it's 180 degrees. I'll just measure this one. So I will go aligning this correctly. So we have a straight line. So we're starting from 0 and we need to go to Inverness again. We need to extend the line so that we can work more easily and accurately. So there we go. And we go 0, 10, 20, 30, 40, 50. So it is 103. So we add in 103. That is 103. So all together, this is gonna be 180 and 103. So there is 283 degrees. So I can say that the bearing of Inverness from Aberdeen is 283, so 283 degrees. I'll bring it closer so we can read it as well. So to summarize, bearings always start from the north. We always measure clockwise. We write the bearings using 3 digits like 283. If there isn't any hundreds in there, we put a 0 in front, so 077 or 042 like here, and it still means degrees. And where we start and where we're going to is the wording. So if the question is to find the bearing of Inverness from Aberdeen suggests that you start with Aberdeen and you go in then to Inverness. Just like the bearing of Edinburgh from Glasgow. So of Edinburgh means we go into Edinburgh. From Glasgow, that's where we're starting. And the bearing of Dublin from Cork means that we're starting with Cork and we go into Dublin. So this summarizes how we use angles when describing position and direction and how we measure angles in degrees. In this video, we'll learn to represent discrete data in tables. What is discrete data? Discrete data is represented using whole numbers, not decimals or fractions. And the type of data that we'd represent using tables vary a lot. So we could have maybe sorting different colors of cubes and creating a table with that data, so showing exactly how many of each color we have. We could represent migration data for a country. We could represent a range of information and data using tables. The example that I will use is that of the number of learners doing a specific course. So we'll have course as the heading for a column. So it could be a level 1 course, level 2 or GCSE. So if it's just these 3 courses that we offer, that's the ones that I'm going to show. Oh, if it's just these 3 that I'm interested in, then I'll show just those. So I will draw a line next to it, then same thing underneath. So I will separate each of these with lines in between. It's not going to look perfect here because I'm using a marker. So what else did we say? Course, and we'll write or represent the number of learners. So with the ruler I would continue the line and then join all of these together at the end. So, and finally I'd have a totals row. So total. So if I'm told that we have 432 level 2 learners, 604 GCSE learners and 250 level 1 learners. So I will place under level 1, I'll place or next to level 1, I'll place 250. Level 2, that's 432. And GCSE, that is 604. Now we'll work out the total. So I've lined them up, so that's easy to work out. 2 and 4 is 6, 5 and 3 is 8, 2 and 4 is 6, and 6 is 12. So 1,286 learners in total doing these 3 courses. So it was important to line these up correctly. So we split these into categories. So whatever courses we offer, we show them one by one, each within each of these boxes or cells, and we'd have the correct heading. So that's course, because all of these are courses. And then what we were interested in was the number of learners. So I wanted to show that for each specific course. So next to each course I'd have the number of learners, and that would be the heading as well of that column. And finally I'd want to show the total. So how many learners are there in total? Now it's really important that we also have a title, so that the person who's going to read the table, they know what we're talking about. So I know we've got courses, we've got a number of learners, but where are these learners? What are we talking about? So I would perhaps say number of learners enrolled on level 1, level 2 and GCSE maths courses at, let's say, maths training provider or whatever it might be. So that shows exactly what you represent when it comes to the number of learners within specific courses, and how you'd represent them. Here we'll learn how to represent data, discrete data in fact, in bar charts. So again, we said discrete data means that we deal with whole numbers, not decimals or fractions. So we'll use the same scenario, the same context we had before, looking at the number of learners enrolled on level 1, 2 or GCSE maths courses at a specific place, and we'll show the same data using a bar chart. So I'll start off by drawing what we call the horizontal axis. So it's horizontal, like the horizon. and I'll use a different color. So there we have the horizontal axis. I'll try and move the camera a bit so that it looks exactly horizontal or closely. And then we have the vertical axis. Okay, so here on the horizontal axis we'll show the different types, like we have here the different courses, whereas on the vertical axis we typically show the numbers. So they start from 0 normally, and we've got to go up to 604, so that's the highest number that we have. So we've got to think of maybe 650 or 700 being represented. So it's got to be equal divisions, so equal parts each time, going up by the same amount each time. So we'd use a ruler, and I could perhaps try and make each of these divisions something like this, so it's exactly the same distance between each point. So I've got 1, 2, 3, 4, 5, and I've got 6, and finally 7. That's what I was after. And if you measure these, that would be the same distance. So we've got 0, then we go to 100. You could decide to go up to 200 or 50 or 150 or 175, whatever you want to, but you're just going to go by the same amount each time. I just find 100 easier to work with. So we go 200, 300, 400, 500, 600 and 700, which is over the 604 that we have here. So now we'll take level 1. So I could show level 1 again. We've got to keep the same width or the same distance here as well. So I could have level 1 here, and then I might leave the same gap or a smaller gap in between these two. I'll leave the same gap or no gap at all. So I could go straight into level 2 here and then level 3. Any of them is possible. So I just have decided to leave a gap, and that gap needs to be the same in between each two of them. So if that's the gap here, this one, it's got to be the same here as well. So we'll see how that looks like in a second. So 2, and then we have GCSE. So level 1 goes up to 250. So that's nice and easy to work with. We go to 200, not 300, so it's in between, exactly in the middle of 200 and 300. So you use a ruler to measure that and to draw the lines as well. It's just a bit difficult for me to work with a ruler and a marker at the same time here, because the ruler would wipe the marks. And then for level 2 we go to 432, so it's going to go up to 400, but it's more than 400. Between 400 and 500 is 450. Now I will try and split this or go down a bit, so it's going to be under 450 because this is 432. So that's probably around here. And if you have lined paper or squared paper, that's going to be easier to calculate. So you've got to compare it. between, as we said, between 400 and 500, right in the middle is for 450. So 430 means you're going down. So that space between 400 and 450, try and split it into 5 equal parts and go to 430 through that. And 432 is just over that, but it won't be seen as clearly in here. So that is level 2, and then we've got GCSE, which goes to 604, so it's roughly about 600. So I would use a ruler to line this up and go up to the right point to meet this other point here. So it's got to be in the same level, and then keeping the same gap. I'll do the same here, and then join these dots. So we've actually drawn the bars, and you can color them in. You can be the same color or different colors, or can put lines in them, so you can line them if you want, or put dots. And so these are level 1, level 2 in GCSE. What are they? The courses. And what are these? What do they tell us? This is about the number of learners. And in terms of a title, I'll just put the same title as what we put for the table, like number of learners enrolled on level 1, level 2 and GCSE maths courses at Maths. So we've included everything so that the reader is able to actually read this bar chart and understand what we're talking about and how many and so on. And I just want to include a slightly more complicated scenario as well, which you could be given. So let's suppose you're given the number of learners, and that is for a specific year, let's say for year 2018, and then you're given some other numbers for year 2019. So you'd include in the table, you'd include another column. So let's just add some. So that would be the same heading, but just year 2019. So let's say we've got 310, and then we've got 376 in here. We've got 645 over here. So what we can do now, how can we represent that in a bar chart? So we'll represent it next to each of these bars. So level 1 will have another bar here for level 1, which shows 2019. So that would be 310. So I'll show that next to. So I've represented the data for both of the years next to each other. So we've got level 1 in red 2018 and in blue 2019. So we've got to include the key. That's what we call the key, which shows the difference between the two colours, between the two bars next to each other. So level 1 going across the two bars, because they both of them are for level 1, and then both of these for level 2. So the writing must be across the two, the width of the two bars, and GCSE as well. So then, so we've got, as we said, 250, and you can see a rise in 2019 going to 310, so that's just over 300. And then In level 2 numbers, we've got 432, and there we see a drop in 2019, and from 2018 to 2019 there is a rise in GCSE number of learners. In terms of the title, because we need to include the title, then we'd have something very similar to this: a number of learners enrolled on level 1, level 2 and GCSE maths courses at Maths in 2018 and 19. So we've got to be specific. What is it about? And include the years as well. And we've labeled the 2 axes as well. So we still have courses just like we had before, and number of learners on this side, just like we did when we had only the 2018 data. In this video, we'll learn to represent discrete data in line graphs. So I've kept the axis that I used for the bar chart, so that's exactly the same way that we do it for line graphs. So we've got level 1, level 2 and GCSE, so they're all courses. So what we've done here is labeling the horizontal axis, and we've labeled the vertical axis as well. So we've got number of learners: 100, 200, 300, 400, 500, 600, 700. So going up in 100 each time, because the highest value that we have is 604 for the 2018 learners. So I will represent that. So we'll assume that we have only the 2018 data to begin with. So I'll hide the 2019 data. So just like with the bar charts, I go, that's 250, so I'll go, where is 250? Level 1, that's the middle of level 1. 250 is right here, just in between 200 and 300. And we've got level 2, 432, so 432 is around here. So I'm just putting a dot, not a whole bar. And 604, so that's going to be just over 600. So that is the data that we have. So I've just plotted those pieces of data, and what is tempting to do is just connect these dots and make a line to make a line graph. However, that's not right. I cannot create a line graph with what I've got here, because a line graph shows that change from one point to the other, and that's not here. That's not being shown here. We haven't got time. We haven't got the change in time. So we have level 1, level 2 in GCSE. Yes, we can see that we have more learners on the GCSE courses. Yes, we can see that we have more level 2 learners than level 1, or less in level 1 and level 2 than GCSE. However, this is not showing any continuity or any change across time or over time. So that is not any data that we can represent using line graphs. You could represent it as a bar chart, but not as a line graph. So for that reason, I will take this off, and I'll show you what I can actually show using a line graph. And I gave you a clue when I said we're looking at things over time. So I'm going to show the 2019 data as well. So if we pick a specific level, let's say level 1, so we represent the number of number of learners enrolled on level 1 courses at Maths in 2018 and 2019. That is something that I could do. So I'll tick off the levels and I'll go okay, 2018 and 2019. So that's years. So in 2018, level 1 was 250, so we got to 250. In 2019, that was 310, so we got to 310. Now that shows a change between 2018 and 2019. So over time, we can see that shift, things going up or down. So I could connect these two dots and make or create that line graph. Now, if I had data for 2010 as well, so I would go 430 for level 1. So let's go to 2020, sorry, 2020. So we go to 430, so that is around here. Again, that's another increase, and we can show that change over the years. In more complicated line graphs, you could have different levels. So I've done in black level 1, for example. So I'll do that as a black line. Or you could even have a cube there, a square like I did, or a cube. And let's do level 2 in blue. So level 2 over the years, we go 432 in 2018, so 432, 376, 376, so there is a drop. And then we go to 400 in 2020, so that goes to 400. So again, connect the dots and you can see what's happened over time. And if we do GCSE in red, then we can go 604 2018, 645 in 2019, and maybe goes to 700 in 2020. So again, by connecting the dots, we can see that increase year on year, that change year on year. So typically a clue for you is in a line graph, if you've got time here on the x-axis or the horizontal axis, that means that it is possible to represent the data using a line graph. In this video, we're going to represent discrete data in pie charts. If you haven't already done so, please have a look at the videos on how to represent data in tables, bar charts, and line graphs. So pie charts, just like the name suggests, it does look like a pie. So it is a circle that we'll need to start drawing. So that's the first thing. I'll start with a dot, which is the center of the circle. And I'll actually bring this forward so that we can see it more clearly, and I'll zoom in. So I've got a dot that I'm going to start with, lining it up correctly and drawing a circle. So starting from 0, going to 180, and then reversing this, turning it upside down. So again, keeping the center where it is, and then we have 0 and 180 just where they need to be. So I will now draw the rest of the circle. You could use a compass to do this as well. So I've got the circle and I've got the center of it as well. So what I'm going to represent is the number of learners doing level 1, level 2 and GCSE in year 2018. So it is this column that I'm looking at. So we've got level 1 250, level 2 432 and GCSE 604. That's out of the total, which is 1286, because we're going to need that to work out how many degrees will each of these slices or sectors be represented by. So let's start with level 1. So that is 250. 250 out of 1286. So that's one way of working it out. That's what it is, 250 out of 1286. So that gives us the decimal. So I'll use a calculator to do that. So we go 250 divided by 1286. So that gives us the fraction, and then we have the decimal. So that's what part of the circle level 1 represents. So it is like looking at 20%. So roughly it's like splitting this circle into 5 equal parts, and almost 1 part will be represented by level 1. But we don't want to round the figures here. We don't want to estimate. What we want is the exact number of degrees. So for that reason, that's what part of the circle. And we know that there are 360 degrees in a full circle. So what I'm going to do is I'm going to multiply this by 360. And that gives me the number of degrees. So times 360 gives me if I round this now, because I have 2, that's going to be 70 degrees. So I like to start from the top, but you could start anywhere really. So now I'll line this up, so that needs to go in line with the protractor, and that end of the line, or the center of the circle, should meet with the center of the protractor as well. So that's the point there, right on top, and we need to go to 70 degrees. So we start from where the line is, wherever the base. So we go 0, 10, 20, 30, 40, 50, 60, 70, and that's where I need to stop, at 70. Now you can see numbers underneath as well, but we start from 0, just like we do with the ruler. So I will follow the numbers at the top in this case. If my line was here, then I would start in this direction and look at numbers from 0, 10 and so on. So we've stopped here at 70. So we'll just join the 2 dots together. So that should be what represents level 1. So now we'll look at level 2. So we'll do exactly the same, follow the same procedure. So go level 2 is represented by 432 out of 1286, which is a total, times by 360, which is the total number of degrees. So 432 divided by 1286 times 360, that gives us 100 121 degrees. So now we'll start from where I finished with level 1. So again, lining it up, center matching the center of the circle, and we go from 0, we need to go to 121. So 121 is just here. Again, connecting this with the center. Now, what we have here is the GCSE part, but we want to make sure that we've got it right. So I'll do the calculation for GCSE as well, although it's the only one that we've got left. So we've got the number of GCSE learners is 604 out of 1,286 times 360, and let's see if it gives us the number of degrees we have here allocated for GCSE. So 604 divided by 1,286 times 360, that gives us 169 degrees. So let's measure this. So, right, so going from 0 to, that's just under 170, which shows that we did the rest of the calculations right as well. So this is the GCSE part. So to make this clear, we would color them in different colors. So level 1, level 2, and GCSE. We'd give this a title, so I would say number of learners enrolled on level 1, 2 and GCSE maths courses at Maths in 2018. So it's very clear that we're talking about a specific year. So the title would be exactly the same one that we used for the table and the bar charts. Now, if we would like to compare two different years using a pie chart, what we'd do is next to this we'd have another pie chart representing level 1, level 2 and GCSE, just like we did here, but with the 2019 data, and that should show clearly if the sector for level 1 is larger in one of them, you can see that there are more learners in that particular year. If you'd like to have a go at representing the 2019 or 2018 data, all three. In this video, we'll learn to group discrete data and represent it graphically. What is discrete data first? Discrete data is different from continuous data in that we don't have numbers like 4.83, so different values which include decimals as well, whereas discrete data is more like specific values. If you look at sizes of clothes, it can only be, let's say, 6, 8, 10, 12, 14 and so on. They can't be 12.3. So those sizes of clothes are called discrete data. They can't be continuous like the decimals. So the values that I have here, they are marks received in a test by students. So a mark can only be 7, it can't be 7.2, for example. So you can only get 6, not 6.3. So it's most of the time whole numbers and specific values. So we'll need to group these data, this set of data, and represent it graphically. So what I have done, I've grouped them into fail, pass, merit and distinction because that's how I can input them in the system. So I have looked at how many learners got between 0 and 3, so 0, 1, 2 or 3, and it was, there's one here, 2 and another one there, so 3 in total. So that's why I put 3. So frequency means how many of them or how often this is appearing, and pass is either 4 or 5, so I went 1, there is a pass there, 2, 3, 4 passes, and merit either 6 or 7, so I went 1, 2, 3, 4, 5, 6, 7, so 7 in total. And distinction, there was just 1 because there was only 1 8 in there. So I've grouped the discrete data here and I'm going to show it graphically. So in this graph I'll have these different groups. So we have fail, we have pass, merit and distinction. So it goes only up to 7, so I'll start with 0, then 1, 2, 3, 4, 5, 6, 7. So how many received fail? There was 3 of them, so 1, 2, 3, and I've just shown that. And there we have pass. So there was 4 of them, and merit was 7. And distinction just 1. And I can double check. Now what I can add here as well is I could have the number of marks. So instead of saying grade and frequency, I could have frequency there and number of marks, and then I would put marks from 0 to 3, so 0 to 3, and then here it'd be 4 to 5, 6 to 7, 8 to 9. But either way is perfectly fine. So either saying the marks and putting the marks down, or saying grade and put in fail, pass, merit or distinction. And of course we'd need a title. So here we'd write something about what this graph represents. So something along the lines of marks that a class received in their maths test, for example, or the grade that learners received in a maths test in a class at college. Or if you want to be a bit more specific, you can write the class title or number. In this video we'll learn to find the mean and the range of a set of quantities. When do we use this and what do this mean? Mean and range are types of averages, so we use them to work out maybe the average spending in a week or a month. So things that you'd want to know roughly on average, something like a mid-value that tells you how much you've spent or earned. So we'll start with an example. So let's say this is the amount that I spent on lunch during the week. So Monday, £3, Tuesday, £2, Wednesday, £4, Friday, I spent 5, whereas on Thursday I spent 4 again, and of course I didn't spend any on Saturday and Sunday because I was off. So if we try and show this in a graph, the amount I'm spending each day is changing, apart from Wednesday and Thursday. So there is 0, £1, 2, 3, 4, and the maximum is 5. So spending in pounds, and that's day of the week. So Monday, Tuesday, Wednesday, Thursday, Friday, and that's it. So on Monday I spent 3, so that amount should go up to 3. Tuesday I spent 2, so going down. Wednesday that was 4, so going up again. And Thursday was the same as Wednesday, so again £4. And Friday was 5, so the highest on Friday. Right, so as you can see, the amount is changing, and what I'm after is actually an average amount. What's that average amount? So that's in between, highest and lowest, roughly consistent with the rest of the data, so somewhere in the middle. And I'm thinking it's perhaps around here. It's not the highest, it's not the lowest, somewhere here. It's an estimate that I'm getting here, but to work out exactly, there is a way. There is a way, and we need to take into account all of them, all of the amounts, and if I find the total and then share them equally or divide by how many days there are, that's going to give me how much on average I've spent each day. So taking into account the highest and the lowest as well, and every amount. So I'll go Monday 3, Tuesday 2. I'm ticking them as I go along so that I don't miss any out. Wednesday 4, Thursday 4, and Friday 5. So what is that? 3 and 2 is 5, and 5 is 10, 14, 18. So that is £18 in total for the 5 days. Remember, there's 5 days that I'm going to work and spending, rather than the 7 days of the week, so you shouldn't get confused. And a good indication is looking at how many numbers you've actually input. So that's 18. Now I'm going to divide it by 5. So 18 divided by 5, that is 3.6. So what does that mean? What does that 3.6 mean? It means how much I'm spending roughly or on average every day. So I'm spending £3.60 on average every day, because that's how we write money. It's got to have the 2 digits after the decimal point. So that's the average. And the average, or another word for average, is mean. So these will mean the same thing. When you read the word mean, it means working out an average. So adding them and dividing by how many there are. So average, or the mean average. it's the same thing. Sometimes you have them both of the words and it still means the same thing. So that gave us, it's a pretty straightforward way of working out adding every amount and then dividing by how many there are. Something to pay attention to, let's say one of the days I spent £0, I'd still take it into account. So if that was a 0, I'd go 3, add 2, add 0, add 4, add 5, and then divide by 5 again. Because that day I didn't spend anything, but it's still a day and I'm working out on average, so I need to take that into account. Now we'll look at the range. How do we work out the range, and what does the range mean? The example that I always use is looking at the range of prices in a supermarket. If you go to the cheese section, for instance, you're going to have different prices. You can have higher prices and lower prices. So the range of prices is about the highest and the lowest and what is in between. So that's, or the difference, in other words, that we use in maths, the word difference means the same thing. So we're looking at what is the highest, take away the lowest. The highest spending was on Friday, so I'm working now at the range. So we go 5, take away the lowest was on Tuesday, which was £2. So the range is £3. This was the mean and this is the range. So now going back to the other example, when I tweaked this around and I said on Wednesday if I spend £0, then that would be the lowest amount. So I'd have to look at 5 and 0. 5 take away 0 gives me 5, and that would be the range in that particular case if I spend £0 on Wednesday. So to summarize, with a mean, you take into account all of the data, you add them all up and divide by how many there are. Whereas for the range, you look to find the highest and the lowest and take away the lowest from the highest. In this video, we'll learn to understand probability on a scale from 0 being impossible to 1 being certain, and use probabilities to compare the likelihood of events. So as we said, 0 is impossible. If something is impossible, that's not going to be happening. So that the word that would go in there is impossible. And if the probability of something happening is 1, that means it's certain. And 50-50, 50% is even or equal chance. And between impossible and even chance is something that is called unlikely. So something around 25% is unlikely. So the chances that it won't happen are greater than the chances of it happening. So 25%, if you look at it, compared, there is 75% chance that it's not going to happen, only 25 that is going to happen, and likely is when those chances are about 75%. So most likely it will happen, but it may not as well. So we write probability in different ways. This is the likelihood, so we express likelihood in these words: impossible, likely, even or equal chance, likely, certain. Whereas the probability itself will use the scale and we write it as a decimal, so 0 to 1, 1 whole. So that would be, in the middle would be 0.5, which is 50% or half, and here 25%, or 0.25 as a decimal, and 0.75 as a decimal as well. And as a percentage, so we said decimal, percentage, so 0%, 25%, 50%, 75%, 100%. So that's why something is impossible, because the chances of it happening are 0%, or just 0 as a decimal. And if it's certain, it's got 100% chances of happening, or just 1 as a decimal. If it hasn't got a percentage next to it and it's a 1, it means a whole, 100%. And we also express probability as a fraction. So this here would be 1/4. This one would be half. This one would be 3/4. And of course this is 4/4 or a whole. And this is just 0. So what we'll be looking at now is some kind of events, things that could happen, and put them on this scale based on the probability of them happening. So here is an event: probability of raining tomorrow without checking the weather forecast. So you haven't checked it, you don't know what is the probability of it raining or not, and this is what you'd think. It could rain, but it probably won't. So the chances of raining are 50-50 without looking at the weather forecast. It could rain, but it may not as well. So without checking the weather forecast, I'd put it here. So it's 50% or half, or 0.5, the probability of raining tomorrow without checking the weather forecast. Now we have this probability of a 6-sided dice rolling on 3. So there I have it. What are the possible numbers? We would have either 1, 2, 3, 4, 5, or 6. So the possible outcomes are 1, 2, 3, 4, 5, or 6. So there are 6 possible outcomes. We're looking at the probability of the dice rolling on 3. So which one is that? It's here. That there is only 1 3 in there, so the probability of it is 1 out of 1, 2, 3, 4, 5, 6. So 1/6. 1/6, or 1 out of 6. So where do you position that on a scale? 1 out of 6. So this is a quarter, but 1/6 is less than a quarter. So I'd say about here. It's rather unlikely. So I'll place it here. And I will now look at a couple more examples. Now we've got the probability of a 6-sided dice rolling on more than 3. Which ones of these numbers are more than 3? More than 3 is 4. So 3 is not included because it's more than 3. 4, 5, and 6. So the 1, 2, 3 out of 6 possible outcomes. So 3/6, which is same as a half. So I would place this here. Probability of a 6-sided die rolling on more than 3. Now we've got probability of 6-sided dice rolling on 7. Now we said 6-sided dice has the numbers 1, 2, 3, 4, 5, 6 possible. Is 7 a possibility? No, it's not. For that reason, we're saying that 7 is impossible. So the probability of this happening is 0. So I'll place it here next to the impossible position, or under the impossible position. And if I look at this one, it says this fair spinner has 3 equal sections. What is the probability of landing on red, which is marked with R? So it has 3 possible outcomes. So when you spin it, where is it going to fall, or how many times will it fall on red? And as you can see, all of these 3 possibilities or 3 sections are marked with R, which means red. So no matter how many times you roll it, it's still going to fall on red. So always red, red, red. So probability of this happening is certain, 100%. You roll the spinner, it will fall always on red. So it's got to go to the certain part of the number line or the scale. Now I've got 2 more. Now if I look at this spinner, the spinner has 8 equal sections, as you can see. So 1, 2, 3, 4, 5, 6, 7, 8. The sections are either red, blue, green or white, and we need to find the probability of landing on white. So there are 8 possibilities altogether, so the fraction is out of 8. How many are actually white? So we've got white here, and we haven't got any more whites, so it's 1 out of 8. So 1 out of 8, where is that positioned in this scale? It's smaller than a quarter, but it's more than 0, so I'll put it there in the middle. So it is unlikely, and the probability of it happening is 1/8, or 0.125, or 12.5%. And we've got now a pie chart which shows information about how year 10 students travel to school. So we've got walk, cycle, car and bus. A student from year 10 is chosen at random. What is the probability the student walks to school? So if you look at this, it's got a 90-degree angle in it, which suggests that this is a quarter of the circle. So we're looking at the probability of a quarter, or 25%, or 0.25. So where is that? That is spot on here. So a quarter would go over there. So we've kind of spread out, or we've positioned quite a few probabilities and events, or probabilities of events, and we've compared them with each other. So if you look at this, the probability of the fair spinner falling or landing on red is much greater than the probability of a 6-sided dice rolling on more than 3, because this is certain. This has a 50% chance. And again, if you compare this probability of raining tomorrow without checking the weather forecast to the probability of a student traveling, going to school on foot, walking, that is a smaller probability. So this has a smaller probability than the probability of raining tomorrow without checking the weather forecast. So we've compared, we've placed them on the scale, and we've looked at the probability scale from 0 to 1, the different words that describe the likelihood of events, and I hope this helps you work out probabilities in real life. In this video, we'll learn to use equally likely outcomes to find the probabilities of simple events and express them as fractions. So we looked at these different events in a previous video, and we'll try and recap a bit. So we looked at this event which says this fair spinner has 3 equal sections. What is the possibility of landing on red? So we said they were all red, and for that reason the fraction would be 3 out of 3, because there are 3 possible and all 3 of them are red, which made it certain. So the probability of this happening, or the likeliness of this happening, is certain. The probability is 3 over 3, or a whole, or 1. And we looked at the probability of raining tomorrow without checking the weather forecast, and we said it could be raining or not raining, which is 1 out of the 2. So the probability of raining is 1 over 2, which is half. And so was the probability of the six-sided dice rolling on more than 3. So more than 3, we had 4, 5 or 6, which is 3 of them out of the 6 possible, so which is the same as a half. And we looked at this. The pie chart shows information about how year 10 students traveled to school. A student from year 10 is chosen at random. What is the probability the student walks to school? So walk represents a quarter of the full circle, so that is 1 out of 4, or a quarter, or 25%. And we also work this out as a fraction, because the probability of the spinner landing on white is 1 out of the 8. Only 1 is white out of the 8 possible, so that's 1/8. And we had the probability of a six-sided dice rolling on 3, so 3 was just 1 out of the 6, so that is 1/6. And finally, probability of six-sided dice rolling on 7, we'll write as just 0, because we don't write fractions with 0, so 0 over 7 is not a possibility, so just write 0. So we've expressed probability as a fraction, simple events, and we've written them as fractions, so that kind of helps you place them on the scale as well.